Hello there, and welcome to Life Beyond Scene, where curiosity slows down, details matter, and science takes its time unfolding. Tonight, we are stepping toward the shoreline, toward a place that often looks safer than it truly is. Not the roaring open ocean with its rolling swells and distant horizon, but the still water tucked quietly behind sandbars and coral reefs. A lagoon, calm on the surface, sheltered from waves, often shallow, often warm, often mistaken for harmless. It is easy to believe that danger announces itself with noise. We expect risk to come with crashing surf, strong winds, or warning signs posted in bold red letters. The open ocean has a reputation. It is wide, deep, and unpredictable. It has tides that stretch for miles and currents that circle entire continents. It demands respect immediately. A lagoon, by contrast, appears contained, manageable. The water rests instead of surges. The horizon feels closer. The shoreline curves protectively around it. From above, it looks like a quiet pool beside a restless sea. And yet, in many parts of the world, lagoons have proven more hazardous than the open ocean beyond them. Accidents happen in water that seems stable. Illness spreads in water that looks clear. Flooding strikes in places that appear sheltered. The calm surface hides complicated movement underneath, and the very features that make lagoons feel safe can concentrate risks in ways the open ocean does not. If you find this exploration steady and grounding, if you appreciate slow explanations and careful detail, a like or subscription helps this space continue to exist for others who prefer learning without rush or alarm. There is no urgency here, only clarity. When people approach a lagoon, their behaviour often changes. Shoulders relax, voices lower, children wander farther from shore. Inflatable rafts drift without concern. Boats idle gently instead of fighting swell. The absence of large waves gives a sense of control. The water appears shallow enough to stand in. The shoreline encloses it like a bowl, reducing the sense of exposure. Many lagoons are warm, especially in tropical climates, and warmth reinforces comfort. The body interprets warmth as safety. It does not tense the way it does in cold surf, but water does not become simple because it becomes quiet. A lagoon forms when part of the ocean becomes separated by a barrier. That barrier might be a coral reef, a sandbar, a narrow strip of land, or a ring-shaped atoll created by volcanic activity and coral growth over thousands of years. The barrier blocks large waves from entering directly. It reduces visible turbulence. However, it does not eliminate movement. Tides still rise and fall. Water still exchanges with the open sea through narrow inlets. Wind still pushes surface layers. Fresh water from rivers or rain may collect in certain areas. Evaporation may increase salinity. The result is not stillness but confinement. Confinement changes how energy behaves. In the open ocean, wind-driven waves spread outward. Currents disperse across vast distances. Tidal forces distribute across entire coastlines. In a lagoon, space is limited. Openings to the sea are often narrow compared to the total volume of water inside. When tides shift, water must squeeze through those restricted passages. That squeezing effect can accelerate flow dramatically, even when the surface appears flat elsewhere. A swimmer floating peacefully near the centre may not notice the build-up near an outlet channel until movement begins pulling sideways instead of gently rocking. There are lagoons in the Mediterranean, in the Pacific, in the Caribbean, in Southeast Asia, in Australia, and along the coasts of the Americas. Some are famous for turquoise clarity. Others sit beside busy coastal cities. Some are connected to mangrove forests, where roots lace through shallow water. Others lie behind coral reefs that break incoming waves into soft foam. Many are used for recreation because they look predictable. Kayakers favour them. Families wade in them. Resorts advertise them as tranquil alternatives to surf beaches. Tranquility can be real and still coexist with risk. One of the central differences between a lagoon and the open ocean is how water renews itself. The open ocean circulates continuously on a planetary scale. Massive currents such as the Gulf Stream or the Kuroshio Current transport warm and cold water across hemispheres. Wind-driven mixing churns the surface. Deep water rises in some regions and sinks in others. The system is not uniform, but it is dynamic and expansive. Lagoons operate on smaller cycles. If the inlet to the sea is narrow, exchange may be limited. If tides are weak in that region, flushing may be slow. If freshwater runoff carries nutrients into the lagoon, those nutrients may linger rather than dispersing. Lingering substances can alter chemistry. Nutrient buildup encourages algae growth. Algae can bloom rapidly under warm conditions. Some blooms are harmless. Others produce toxins. In the open ocean, harmful algal blooms can also occur, but strong currents may disperse them over the larger areas. In a lagoon, concentration can increase because boundaries prevent easy escape. The water may still look inviting. The surface may still reflect sunlight clearly. Beneath that surface, oxygen levels may fluctuate. Bacteria may multiply. Microscopic organisms may release compounds that irritate skin or affect respiratory systems. The perception of safety often rests on visibility. When waves are small and the bottom is visible through shallow water, people assume stability. Yet shallow water can change quickly. A slight shift in tide may lower the level enough to expose sandbanks in one area, while deepening channels in another. A sandbar that supported weight an hour earlier may soften as currents redirect beneath it. Boats that navigate comfortably at high tide may ground unexpectedly when levels drop. Shallow water also warms more quickly, and warm water can influence both biological activity and weather interactions. Weather behaves differently over enclosed water. During storms, the barrier that blocks waves may trap rising water inside. If wind pushes water toward the lagoon, and there is limited space for it to exit, levels can rise rapidly. Flooding may occur not because waves break over shorelines, but because the basin fills from within. The same protective structure that calmed the surface under normal conditions can restrict drainage under extreme conditions. Water seeks equilibrium, and when confined, it can push outward with force against infrastructure that assumed gentleness. Human development often favours lagoons. Waterfront properties, marinas, docks, and resorts cluster around them. Construction alters natural flow. Channels are dredged. Mangroves are removed. Seawalls replace gradual slopes. Each modification changes how water circulates. Reduced vegetation may decrease natural filtration. Hardened shorelines may reflect waves instead of absorbing them, creating subtle turbulence patterns. Pollution from urban runoff may accumulate more readily in a semi-enclosed basin than in open coastal waters. It is important to separate fear from understanding. Lagoons are not inherently hostile environments. Many ecosystems depend on them. They serve as nurseries for fish species that later migrate to open seas. They support bird populations. They buffer coastlines from wave impact. They can be biologically rich and economically valuable. The issue lies not in their existence, but in assumptions made about them. Assumptions influence behaviour. When people treat a lagoon as equivalent to a swimming pool, they may overlook tides. They may ignore weather forecasts because the water seems insulated from distant storms. They may venture toward narrow inlets without recognising that those channels are points of concentrated movement. They may underestimate how quickly conditions shift after heavy rainfall, when freshwater inflow alters depth and current patterns. In some regions, drowning incidents occur more frequently in sheltered waters than in exposed beaches. The reasons are complex. On exposed beaches, lifeguards are often present. Warning flags are common. Rip current awareness campaigns focus heavily on surf zones. In lagoons, signage may be limited because the water appears calm. Swimmers may spread out over wide, shallow areas without supervision. If a current develops near an inlet, it may not look dramatic. There may be no breaking wave to signal hazard. A person caught in a sideways flow may tire quickly because they did not anticipate resistance. Temperature differences can also create subtle layering. In certain lagoons, especially deeper ones with limited mixing, surface water may warm while deeper layers remain cooler and denser. These layers can resist mixing, creating stratification. If organic material decomposes at the bottom, oxygen can become depleted in lower layers. Fish may move toward the surface. If a strong wind event disrupts the layering, low oxygen water can rise abruptly, affecting marine life. While this process may not directly endanger a swimmer in most cases, it reflects how chemical and physical changes can develop without visible warning. Visibility can degrade rapidly in confined systems. A small disturbance to sediment may cloud water quickly. In the open ocean, suspended particles may disperse. In a lagoon, especially one with fine silt, turbidity may persist. Reduced visibility complicates rescue efforts. It also increases the risk of stepping into unexpected drop-offs or onto sharp coral fragments. Marine organisms sometimes prefer the shelter of lagoons. Jellyfish may drift in and remain trapped by barriers. Certain species of sharks use lagoons as nurseries. Crocodiles inhabit brackish lagoons in some tropical regions. Even in temperate zones, stingrays often bury themselves in shallow sandy areas. None of these creatures are inherently aggressive toward humans, but proximity increases the likelihood of encounters. Again, the issue is not hostility, but concentration. The open ocean distributes, lagoons gather. Gathering is not always visible. A still surface can conceal directional flow beneath. Wind blowing consistently across a lagoon can push surface water toward one side, causing water to pile slightly against the downwind shore. To balance that accumulation, subsurface water may move in the opposite direction. A swimmer floating with the wind may feel little resistance, but turning back may require effort against a current that did not announce itself with waves. Tidal timing matters as well. At high tide, a lagoon connected to the sea through a narrow channel may experience inflow that appears gentle at the surface. As the tide turns and water begins to exit, the same channel can accelerate. The difference between incoming and outgoing flow may be significant. Boaters sometimes underestimate this reversal, especially in areas where tidal ranges are moderate, but channel widths are small. There is also the factor of scale perception. The open ocean communicates depth through horizon distance. The human brain interprets vastness as potentially risky. A lagoon compresses that scale. The far shore appears reachable. The sense of containment reduces caution. Yet depth can vary unexpectedly. Some lagoons contain dredged areas for navigation that drop abruptly from shallow flats. Without wave patterns to signal change, a person wading may step from knee-deep water into over-the-head depth within a few steps. All of these elements build quietly. None require dramatic sound. None demand crashing surf. Risk accumulates through confinement, chemistry, current concentration, biological activity, and human assumption. Understanding this does not remove the beauty of lagoons. It clarifies their nature. They are dynamic systems shaped by barriers, influenced by tides, modified by weather, and often altered by human presence. They require attention, not fear. As we move further into this exploration, it becomes useful to look more closely at why calm water feels reassuring in the first place, and how perception shapes behaviour long before physics or biology enter the picture. When people approach water, their first judgment rarely comes from measurement or scientific knowledge. It comes from sight, sound, and prior experience. A broad stretch of ocean with rolling waves immediately signals power. Noise alone can change posture. Shoulders tense. Steps slow down. People scan for lifeguard flags, warning signs, or local advice. Calm water produces the opposite reaction. When the surface barely moves, when reflections remain intact, when sound fades instead of crashes, the brain interprets the scene as controlled. It does this quickly, often before conscious thought begins. That interpretation developed over long stretches of human history. Still water often meant drinkable water, fishing access, or safe crossing points. Rivers with violent rapids were dangerous. Lakes without strong wave action were useful. Coastal lagoons, sheltered bays, and estuaries frequently served as early settlement sites precisely because they appeared manageable. Over time, humans built an association between calm surfaces and survivability. That association remains deeply ingrained even though modern risks are different. Visual stability is especially persuasive. A flat water surface reflects light evenly. It mirrors sky colours. It creates symmetry that the brain reads as order. When waves distort reflections, the scene becomes visually complex. Complexity often signals unpredictability. People instinctively respect unpredictability. A lagoon at sunset can look almost motionless, like glass. That image encourages confidence. Yet beneath that reflective surface, water may be moving steadily through narrow channels, responding to tidal exchange or wind pressure that is not obvious without instrumentation. Sound also shapes perception. Loud surf generates continuous auditory feedback about energy. You hear the impact before you feel it. Silence removes that cue. Quiet water suggests inactivity even when current speeds are measurable. Divers sometimes report strong subsurface flow in areas where the surface looked placid from shore. Without breaking waves, there is little acoustic warning. Temperature influences perception in another subtle way. Many lagoons are warmer than adjacent ocean waters because they are shallow and enclosed. Warmth relaxes muscles. It lowers physiological stress responses. Cold water, in contrast, triggers caution almost immediately. Entering cold surf can produce an involuntary gasp reflex, reminding the swimmer of vulnerability. Warm lagoon water does the opposite. It invites longer immersion. It reduces awareness of fatigue until tiredness is already present. Familiarity plays a role as well. Pools, ponds, small lakes and sheltered bays often serve as childhood swimming environments. People transfer that familiarity to lagoons without considering differences in scale, tides, or biological complexity. The water looks similar enough. The absence of waves reinforces the analogy. However, unlike artificial pools, lagoons are open systems connected to larger bodies of water through channels that may behave unpredictably over time. Another factor involves control perception. Humans feel safer when boundaries are visible. A lagoon typically has clear edges, a reef line, a sandbar, a curving shoreline. The open ocean lacks those obvious boundaries. The horizon offers no containment. Psychologically, containment implies manageability. Yet physical containment can increase risk by concentrating water movement, nutrients, pollutants, or wildlife within a smaller area. Experience sometimes reinforces misplaced confidence. Someone may swim in a lagoon repeatedly without incident. Each safe experience strengthens the belief that the environment is inherently safe. This is normal learning behavior. However, environmental conditions vary daily. Tidal cycles shift, wind direction changes, rainfall alters salinity and turbidity. Biological populations fluctuate seasonally. A safe experience last week does not guarantee identical conditions today. Tourism marketing occasionally amplifies the perception of safety. Promotional images emphasize stillness, clear water, and relaxed recreation. Safety information may appear in smaller print or not at all. Visitors arriving from inland areas may have limited experience interpreting coastal water behavior. Without waves as a warning signal, they rely on visual calmness alone. The human brain uses heuristics, quick mental shortcuts, to make decisions efficiently. One such shortcut is the calm equals safe rule. It works often enough in daily life to remain useful, but it fails in specific contexts like lagoons. Currents, water chemistry, depth variation, and biological hazards do not always correlate with visible surface agitation. This mismatch between appearance and underlying conditions explains why incidents sometimes occur in places that look tranquil. Cognitive bias contributes further. Confirmation bias leads people to notice information that supports existing beliefs. If someone believes lagoons are safe, they may focus on families swimming comfortably, while overlooking warning signs about tides or wildlife. Availability bias also plays a role. Dramatic ocean rescues receive media coverage because waves are visually striking. Lagoon incidents, often quieter, may receive less attention, reinforcing the idea that they are rare. Group behaviour amplifies individual assumptions. When many people enter calm water without hesitation, others interpret that as social proof of safety. Beaches with surf often display caution flags, lifeguard towers, or audible warnings. Lagoons sometimes lack these visible markers. Without official cues, individuals rely more heavily on group behaviour. Lighting conditions influence perception as well. Midday sun reduces shadow contrast on flat water, making depth changes harder to detect. Evening light can produce glare that hides surface texture. Turbid water after rain may appear similar to deeper water, even when depth varies significantly. Each visual distortion can contribute to overconfidence. The absence of waves also changes physical feedback during swimming. In surf, wave motion provides constant tactile information. You feel lift, push, and pull. In calm water, movement may be more horizontal and subtle. A developing current may not be felt immediately. By the time it becomes noticeable, a swimmer may already be farther from their starting point than intended. Boaters sometimes experience similar misjudgment. Operating a small craft on flat lagoon water feels easier than navigating ocean swell. That ease can lead to reduced vigilance regarding tide tables or weather changes. A sudden shift in wind direction can generate short, steep chop within confined water faster than anticipated. Narrow channels can develop strong flow during tidal transitions, affecting steering control. Children are particularly influenced by calm appearance. They often equate visible waves with danger because adults warn them about rough seas. In a lagoon, absence of waves may reduce adult supervision intensity. Shallow areas encourage exploration, yet drop-offs or channels may exist nearby. Clear communication about boundaries becomes essential, but is sometimes overlooked because the environment looks gentle. Wildlife perception follows a similar pattern. Large ocean animals receive significant attention in media. Lagoon species, often smaller or less dramatic, are perceived as benign. However, organisms adapted to enclosed, warm, nutrient-rich environments can include jellyfish species that tolerate low circulation, bacteria thriving in higher nutrient concentrations, or bottom-dwelling animals capable of defensive stings. Visibility of these organisms may be limited until contact occurs. Another element involves the difference between hazard probability and hazard severity. Open ocean hazards, such as large waves, are severe but visible. Lagoon hazards may be less dramatic individually, but more frequent because exposure increases when people underestimate risk. Frequent low-level hazards can accumulate into significant overall risk. Navigation charts often depict lagoon entrances carefully because of shifting sandbars and tidal currents. Mariners respect these charts. Recreational swimmers rarely consult equivalent data. Information exists, but it is not always accessible in user-friendly form. This gap between available knowledge and public awareness contributes to the illusion of safety. Environmental variability deserves attention. Seasonal changes alter lagoon behaviour. In dry seasons, evaporation can increase salinity, affecting buoyancy and marine life distribution. During rainy seasons, freshwater input can create stratification or turbidity. Storm seasons may raise water levels within enclosed basins, even when offshore conditions seem manageable. Each seasonal factor interacts with human perception differently. Infrastructure can unintentionally reinforce false security. Resorts may build jetties or breakwaters that enhance calmness further. Artificial lighting along lagoon shores can create a sense of urban safety, even when water conditions remain natural. Dock ladders and floating platforms suggest stability similar to pools, though tidal variation still occurs. Technological familiarity also matters. People accustomed to controlled environments such as heated pools or regulated beaches may expect similar predictability everywhere. When natural systems deviate from those expectations, surprise replaces caution. Surprise in water environments can escalate quickly because reaction time is limited. Education about coastal processes often focuses on dramatic phenomena: hurricanes, tsunamis, large rip currents. Subtle processes receive less emphasis in public discourse. Lagoons operate largely through subtlety. Their risks rarely announce themselves loudly. Increasing awareness requires explaining processes that lack visual drama, which can be challenging in fast-paced information environments. Risk communication benefits from specificity. Saying calm water can be dangerous without explanation may sound contradictory and be dismissed. Explaining tidal exchange, chemical concentration, or wildlife habitat patterns provides context that aligns appearance with mechanism. When mechanism becomes clear, perception adjusts more readily. Cultural background shapes interpretation too. Communities with long-standing lagoon interaction often possess local knowledge about safe entry points, seasonal hazards, and wildlife patterns. Visitors without that background may not recognize subtle cues locals take for granted. Dialogue between residents and visitors can bridge that gap, though it depends on communication willingness. Technological aids such as tide apps, weather forecasts, and water quality reports exist, yet many recreational users do not consult them for lagoon visits. The assumption of safety reduces perceived need for preparation. Encouraging routine information checks, similar to checking weather before hiking, can improve safety without reducing enjoyment. Lighting again becomes relevant near dusk. Calm water reflects fading light evenly, making it difficult to judge distance. Swimmers may venture farther than intended because landmarks appear closer in reflection. Returning against a subtle current in low light increases fatigue risk. Fatigue itself is often underestimated in warm, calm water. Without waves forcing periodic rest or orientation adjustments, swimmers may continue longer than planned. Gradual fatigue combined with unnoticed drift can create situations where returning to shore requires more effort than expected. Equipment choices reflect perception as well. People entering surf often wear flotation devices, use surfboards, or remain near lifeguard zones. In lagoons, minimal equipment is common. Lack of flotation reduces margin for error if conditions change. All of these psychological, cultural, environmental, and biological factors combine to produce the illusion of safety. The illusion does not arise from ignorance alone. It emerges from evolutionary conditioning, visual cues, social behavior, and incomplete information. Recognizing the illusion allows for adjustment without eliminating enjoyment. Understanding why calm water feels harmless leads naturally into understanding what lagoons physically are and how they form, because the structure of these environments explains why appearance and reality sometimes diverge. A lagoon is not simply a calm body of water beside the sea. It is a specific type of coastal system formed through geological and biological processes that create partial separation between ocean water and land. The key feature is enclosure. A lagoon exists where ocean water becomes trapped or semi-trapped behind a barrier. That barrier might be a coral reef, a sandbar, a barrier island, a spit of sediment, or a ring-shaped atoll formed from coral growth over submerged volcanic rock. The result is a shallow body of water that remains connected to the sea but not fully exposed to it. The word itself comes from the Italian laguna, referring to the shallow waters around Venice. Those waters are technically a lagoon system shaped by sediment deposition and tidal exchange with the Adriatic Sea. Around the world, lagoons take different forms, but they share certain physical characteristics. They are coastal, they're relatively shallow compared to the open ocean, and they are separated from direct wave action by some form of natural barrier. Formation begins with movement. Coasts are dynamic environments shaped by waves, currents, tides, and sediment transport. Sand carried by longshore currents can accumulate into narrow strips parallel to the shoreline. Over time, these strips can grow into barrier islands or sandbars. When that happens, water between the mainland and the barrier becomes partially enclosed. If openings remain, tides continue to move water in and out through channels. That partially enclosed water body becomes a lagoon. In tropical regions, coral reefs often create lagoon systems. Coral polyps build calcium carbonate structures that grow upward towards sunlight. Over thousands of years, these reefs can form continuous ridges. If a reef grows around the perimeter of a volcanic island that later subsides, the central island may sink below sea level, leaving a ring-shaped reef with a central lagoon. This structure is known as an atoll. The lagoon inside the ring is protected from direct ocean swell, but it remains connected to the sea through passes in the reef. Depth is an important factor. Lagoons are usually shallow, often only a few meters deep, though some may reach greater depths near inlets or dredged channels. Shallow depth allows sunlight to penetrate to the bottom, which encourages plant growth such as seagrass and supports diverse ecosystems. However, shallow depth also means temperature can change more rapidly than in deeper ocean water. This responsiveness to environmental conditions makes lagoons biologically productive but physically variable. Salinity in lagoons can vary significantly. Some lagoons are primarily marine, meaning their salinity closely matches the ocean because tidal exchange is strong. Others receive fresh water input from rivers, rainfall or groundwater, creating brackish conditions. In arid climates with high evaporation and limited inflow, salinity can increase beyond ocean levels. These shifts influence the types of organisms that can survive there. Fish, crustaceans, mollusks, and birds often rely on lagoons as breeding or feeding grounds because of this biological richness. Water movement inside a lagoon differs from open ocean circulation. In the ocean, large-scale currents are driven by wind patterns, Earth's rotation, and density differences caused by temperature and salinity. In a lagoon, circulation is typically governed by tides, wind-driven surface flow, freshwater inflow, and the geometry of the basin. Because the area is enclosed, water exchange may occur through only one or two narrow channels. These channels act like valves, controlling how quickly water enters and leaves. The rate of flushing, meaning how quickly lagoon water is replaced with ocean water, determines many of its characteristics. A lagoon with wide, deep inlets may flush efficiently, maintaining stable salinity and oxygen levels. A lagoon with narrow or shallow openings may flush slowly, allowing nutrients and sediments to accumulate. Slow flushing increases the potential for algae growth and chemical changes. It also means that pollutants introduced into the lagoon may remain longer than they would in open coastal waters. Sediment dynamics are central to lagoon identity. Rivers may carry fine particles into the basin. Wind can resuspend bottom sediments. Because wave energy is reduced by the barrier, sediment settles more easily than in exposed surf zones. Over time, this can create soft, muddy bottoms in some lagoons and sandy flats in others. These bottom types affect both marine life and human activity. Soft sediments may reduce water clarity when disturbed. Sandy bottoms may shift under tidal currents. Barrier stability is not permanent. Storms can breach sandbars, creating new inlets or widening existing ones. Over years or decades, sediment deposition may close channels partially or entirely. As geometry changes, circulation patterns adjust. A lagoon that once flushed quickly may become more stagnant. Another that was nearly isolated may suddenly experience stronger exchange after a storm event reshapes its entrance. Climate influences lagoon formation and behaviour. In tropical climates, coral-based lagoons dominate. In temperate regions, sedimentary lagoons behind barrier islands are more common. In colder climates, lagoons may freeze seasonally, affecting circulation and oxygen levels. Rising sea levels alter lagoon boundaries by submerging barriers or expanding connections to the sea. These long-term changes can modify risk patterns for nearby communities. From a hydrological perspective, a lagoon is a semi-enclosed basin connected to the ocean by at least one restricted opening. That restricted opening is central to understanding how lagoons differ from bays. A bay is typically more open to the sea, allowing larger waves and more extensive circulation. A lagoon, by contrast, is shielded more fully from direct ocean swell. The shielding creates the calm surface appearance often associated with safety, yet it also defines the confined nature that can concentrate environmental processes. Ecologically, lagoons serve as transition zones between terrestrial and marine environments. Mangrove forests frequently line tropical lagoon edges. These trees anchor sediment and provide nursery habitat for fish and crustaceans. Seagrass meadows stabilize sandy bottoms and produce oxygen during photosynthesis. Birds use shallow flats for feeding. Because nutrients can accumulate in semi-enclosed water, primary productivity may be high. This productivity supports complex food webs. However, productivity has limits. Excess nutrient input from agriculture, sewage, or urban runoff can push lagoon systems beyond balance. Algal blooms may develop. Some blooms reduce oxygen when they decay, leading to hypoxic conditions that stress fish and invertebrates. In extreme cases, fish kills occur. The same confinement that allows ecological richness can amplify ecological stress. Water temperature variability deserves attention. Because lagoons are shallow, they respond quickly to solar heating and nighttime cooling. In hot climates, water may become significantly warmer than adjacent ocean waters. Warm water holds less dissolved oxygen, affecting aquatic organisms. Temperature differences between lagoon and ocean water can also drive density-based flow when exchange occurs, influencing current direction during tidal cycles. Wind plays a strong role in lagoon dynamics. A steady wind blowing across a lagoon can push surface water toward one shore, slightly raising water level there. This setup effect creates a pressure gradient that drives return flow beneath the surface. In larger lagoons, wind-driven circulation patterns can form predictable loops. In smaller lagoons, wind may push water toward an inlet, increasing flow velocity through that opening. These wind effects are often underestimated because the water surface appears smooth compared to open ocean waves. Tides interact with lagoon geometry in complex ways. When tide rises in the open ocean, water flows into the lagoon through inlets. The speed of that inflow depends on tidal range, inlet width, and basin size. When tide falls, water exits. Because the lagoon has limited openings, flow through those openings can accelerate significantly compared to surrounding areas. This acceleration may not be visible from a distance, especially if the rest of the lagoon remains calm. Chemical gradients may develop as well. Fresh water entering from rivers tends to be less dense than seawater. It can form a surface layer over saltier water beneath. If mixing is weak, this layering can persist. Sudden mixing events, such as storms, can disrupt layers and redistribute oxygen and nutrients. These processes influence biological activity and water clarity. Human interaction shapes lagoon structure further. Dredging for navigation deepens certain areas, altering circulation patterns. Construction of causeways or bridges may restrict flow further if openings are limited. Removal of natural vegetation reduces filtration capacity. Conversely, restoration projects sometimes reopen inlets or replant mangroves to improve water quality and resilience. In some regions, lagoons are used for aquaculture, including shrimp or fish farming. These activities can increase nutrient levels if waste accumulates. Management practices determine whether lagoon ecosystems remain balanced or shift toward degradation. Understanding what a lagoon is requires recognizing it as a system defined by partial separation and limited exchange. It is neither fully ocean nor fully landlocked. It exists in between. That in-between state produces characteristics that differ from both open sea and inland lakes. It produces calm surfaces under many conditions, yet it also creates confined pathways for energy and matter. Because barriers block direct wave impact, people often perceive lagoons as simple bodies of water. In reality, their simplicity is visual rather than structural. Beneath the surface lies a network of processes driven by tides, wind, sediment, freshwater input, biological activity, and human modification. Each lagoon has its own configuration, shaped by geography and history. The physical structure of barriers and inlets leads directly to how water movement behaves inside these systems. To understand why hazards can develop unexpectedly, it becomes necessary to examine how those barriers not only protect, but also trap and redirect energy within the lagoon basin. A barrier looks protective. That is its primary visual message. Whether it's a coral reef crest rising just below the surface, or a sandbar stretching parallel to shore, the barrier absorbs wave force from the open ocean. Incoming swells break against it, lose height, and disperse energy before reaching the interior water. From the shoreline inside the lagoon, the ocean may be only a few hundred meters away, yet the surface remains relatively flat. That flattening effect reinforces the sense that the barrier has neutralized risk. What the barrier actually does is redirect and concentrate energy rather than eliminate it. When waves approach a reef or sandbar, they break because the water becomes shallower. As wave height increases relative to depth, the wave destabilizes and collapses. The energy from that collapse does not disappear. It transforms into turbulence, heat, and horizontal water movement. Some of that water spills over the barrier into the lagoon. Some returns seaward as backwash. The volume that enters must eventually exit. Because the lagoon is enclosed except for limited openings, that return flow becomes focused through specific channels. Those channels function as bottlenecks. A bottleneck in fluid dynamics means that a large volume of water must pass through a restricted space. When cross-sectional area decreases, velocity increases to maintain continuity. This principle is not theoretical. It is measurable. If 1,000 cubic meters of water enter a lagoon per minute during rising tide, and there is only one narrow inlet available for exit during falling tide, the speed of water through that inlet will increase, relative to the broader basin. From inside the lagoon, the surface away from the channel may remain calm. Near the bottleneck, however, flow can be strong and directional. Swimmers or small craft caught in that concentrated current may struggle, because the surrounding water appears tranquil, offering little visual cue that a strong horizontal force exists nearby. Barriers also create resonance effects. When wind or wave energy repeatedly pushes water toward the lagoon side of the barrier, the water level inside can rise slightly. This setup effect increases pressure against the barrier and drives flow toward inlets. If wind direction persists, the lagoon may develop a sustained internal circulation pattern. Water piles up on one side and drains on another, creating a loop. The barrier defines the boundaries of that loop, preventing dispersion across open sea. Storm conditions amplify these dynamics. During high wind events, ocean waves breaking over a reef can transfer large volumes of water into the lagoon. If the lagoon's outlets cannot drain that water quickly enough, interior water levels rise. This rise may be gradual at first, then accelerate as wind continues. Infrastructure along lagoon shores may flood not because ocean waves overtop directly, but because trapped water accumulates inside the basin. In sedimentary lagoons behind barrier islands, the sandbar itself shifts over time. Longshore currents move sand parallel to the coast, building and reshaping the barrier. After storms, new inlets may open where waves breach the sandbar. These inlets initially allow strong exchange between lagoon and ocean. Over months or years, sediment may partially close them. Each change alters how energy enters and exits the system. A lagoon that once had 2 outlets may later have only 1, doubling the volume of water moving through the remaining channel during tidal exchange. Coral reef barriers introduce additional complexity. Reef crests often contain passes, naturally deeper gaps where boats can navigate. These passes are typically the primary exchange points between lagoon and ocean. because the reef blocks most wave energy elsewhere, the passes become the main routes for water flow. During falling tide, water drains through them. During rising tide, water surges inward. The difference in water level between lagoon and ocean determines flow direction and strength. A small vertical difference across a narrow pass can generate significant horizontal velocity. Velocity becomes hazardous not only because of strength, but because of expectation. In open ocean surf zones, people anticipate strong water movement. In lagoons, expectation is different. A narrow pass may appear calm if wind is light and surface ripples are minimal. Underneath, however, water can move steadily in one direction. Without breaking waves to reveal motion, swimmers may not recognize drift until they are close to the pass. Barriers also trap floating debris and biological material. When wave energy pushes organic matter into a lagoon, the barrier reduces the likelihood of immediate dispersal back to sea. Floating algae, driftwood, or even pollution can accumulate against interior shorelines. In some cases, this accumulation affects water quality. In others, it alters navigation paths for small boats. Thermal energy is similarly retained. Shallow lagoons warm quickly under sunlight. The barrier reduces mixing with cooler offshore water, so heat remains longer. Warm water influences density and circulation. Because warm water is less dense, it tends to remain near the surface. If cooler ocean water enters through a channel at depth, layering can occur. The barrier prevents full mixing across wide areas, allowing stratification to persist until wind or strong tidal exchange disrupts it. Energy trapping is not limited to physical movement. Acoustic energy behaves differently inside enclosed basins. Sound waves reflect off boundaries rather than dissipating across open sea. While this may not directly create hazard, it affects how marine animals communicate and navigate, influencing ecological patterns within lagoons. Wave reflection inside the lagoon can also create standing wave patterns, especially in elongated basins. When wind pushes water toward one end, it may slosh back when wind subsides. This oscillation, known as a seiche, can cause water level fluctuations independent of tidal cycles. In narrow lagoons, seiches can amplify movement near ends or constrictions. The barrier defines the container in which this oscillation occurs. Human-made barriers intensify these processes. Seawalls, jetties, and causeways change shoreline geometry. Hard surfaces reflect wave energy rather than absorbing it. Reflection can increase localized turbulence near structures. If jetties narrow an inlet, they increase flow speed during tidal exchange. Engineers design these structures with navigation and erosion control in mind, but the hydrodynamic consequences extend to swimmers and small vessels as well. When considering energy trapping, it is useful to compare lagoon scale with ocean scale. The open ocean distributes energy across vast distances. Even strong currents have room to spread. In a lagoon, energy is confined. Confinement increases interaction between water and boundaries. Boundaries redirect flow rather than allowing it to dissipate freely. Rainfall events highlight this confinement. Heavy rain over land drains into lagoons through rivers or runoff channels. If the lagoon's ocean outlet is narrow, freshwater input may temporarily exceed outflow capacity. Water levels rise and flow through the outlet intensifies. The barrier prevents lateral escape, forcing vertical rise and concentrated horizontal discharge. During these periods, currents near outlets may strengthen beyond typical expectations. Barriers also influence sediment deposition patterns. When wave energy is reduced inside the lagoon, fine particles settle. Over time, this creates shallow flats that alter circulation paths. As depth decreases in certain areas, flow concentrates into remaining deeper channels. These channels become more defined bottlenecks. The process can be gradual and unnoticed by casual observers. In tropical atolls, the lagoon interior may appear expansive and calm, yet tidal exchange through reef passes can generate visible whirlpools or surface streaks during strong flow. Local communities often know which passes are safe for crossing and which require timing with slack tide. Visitors without this knowledge may misjudge. The geometry of a lagoon determines how energy distributes. A circular lagoon with multiple inlets behaves differently from a long, narrow lagoon with a single outlet. In elongated lagoons, water pushed by wind can travel along the entire length before encountering resistance, increasing momentum. When it finally reaches the bottleneck, acceleration may be pronounced. Barrier height relative to sea level matters as well. During exceptionally high tides or storm surge events, water may overtop low barriers, entering the lagoon across a broad front rather than through channels. Once inside, however, retreat still funnels through limited exits. This mismatch between entry width and exit width enhances concentration of return flow. Energy can be stored temporarily in water level differences. If the ocean tide rises faster than the lagoon can fill through its inlets, a temporary gradient forms. When equilibrium approaches, rapid inflow may occur. Similarly, when tide falls rapidly offshore, the lagoon may drain with delay, then accelerate discharge as the gradient increases. These transient states create pulses of stronger current. Wind interacting with barrier geometry can generate localized upwelling or downwelling near edges. Upwelling brings deeper water upward, potentially affecting temperature and oxygen levels. Downwelling pushes surface water downward. Both processes are subtle and rarely visible without instrumentation, yet they contribute to internal energy redistribution. Understanding barriers as dynamic structures rather than static shields changes interpretation. The barrier protects against direct wave impact, but also defines the system's constraints. Constraints shape behavior. In physics, constraints often produce complexity. The lagoon is a constrained basin where water movement must obey the limits imposed by its boundaries. This constrained behavior explains why lagoons can feel stable, yet respond sharply to changes in tide, wind, or storm intensity. The apparent stillness represents equilibrium under certain conditions. Shift those conditions, and the system redistributes energy quickly within its confined space. The idea of bottlenecks extends beyond inlets. Narrow mangrove channels, artificial marina entrances, and dredged cuts through sandbars all act as energy funnels. When water seeks to equalize levels between regions of slightly different height, it flows through these constrictions. Speed increases where width decreases. People anchored near these zones may notice unexpected drift. The trapping and redirection of energy by barriers sets the stage for another critical aspect of lagoon behavior. The currents that form within the basin itself, often invisible until they are felt. Understanding how these internal currents operate reveals why calm surfaces cannot be taken as reliable indicators of safety. Water does not need waves to move. That fact often surprises people because waves are the most visible expression of ocean energy. When waves are absent, movement becomes harder to detect. Lagoons specialize in this kind of quiet motion. The surface may look nearly still while currents flow steadily underneath, shaped by tides, wind, density differences, basin geometry, and restricted connections to the open sea. The calm surface conceals horizontal movement that can carry swimmers, sediment, nutrients, and even small boats without obvious warning. The first driver of hidden currents is the tide. Even if waves from the open ocean are blocked by a reef or sandbar, the gravitational pull of the moon and sun still raises and lowers water levels. When the ocean tide rises, water flows into the lagoon through available openings. When it falls, water flows out. Because these openings are usually narrower than the lagoon itself, the incoming or outgoing water concentrates into defined streams. Away from those openings, the surface may show only faint ripples, yet subsurface flow continues as the lagoon equalizes its water level with the sea. Tidal currents inside lagoons do not always move in straight lines. The basin shape causes water to circulate in loops. If one side of the lagoon fills first, water may spread laterally before exiting elsewhere. This circulation can create zones where currents intersect or rotate slowly. These rotating areas are not dramatic whirlpools, but they can produce persistent drift. A floating object released in such a zone might trace a slow arc rather than travelling directly outward. Wind adds another layer. Even gentle, steady wind exerts force on the water surface. Because lagoons are shallow, wind-driven surface flow can influence the entire water column more easily than in deep ocean areas. Surface water pushed downwind accumulates slightly against the far shore. That accumulation forces return flow beneath the surface toward the upwind side. This two-layer circulation often goes unnoticed because only the surface direction is visible. A swimmer floating with the wind may drift comfortably until attempting to return, at which point resistance from subsurface return flow becomes apparent. Temperature and salinity differences create density-driven currents. Warmer water is less dense than cooler water. Fresher water from rainfall or rivers is less dense than salty seawater. When these differences exist, layers form. Lighter water sits above heavier water. If mixing occurs, gravity tries to restore equilibrium, generating horizontal and vertical movement. For example, after heavy rain, a thin layer of fresher water may spread across the lagoon surface. When tide changes bring saltier ocean water through an inlet, the denser seawater may slide beneath the fresher layer, forming an undercurrent invisible from above. Such stratified flow can surprise divers and swimmers. At the surface, conditions seem gentle. A metre below, water may move in a different direction entirely. Divers sometimes describe feeling a sideways push at depth, even when the surface remains calm. This is common near reef passes or dredged channels where denser ocean water intrudes into a lagoon. Sediment interaction also contributes to hidden currents. Fine sediments on lagoon bottoms can shift under mild flow conditions. When currents accelerate slightly, they resuspend particles, reducing visibility. Reduced visibility can make it harder to recognize current direction, because visual reference points disappear. A swimmer in turbid water may not notice gradual drift until the shoreline position changes noticeably. Seiches, a form of internal oscillation, occur in some lagoons. Wind or pressure changes can push water toward one side of the basin. When the forcing stops, water sloshes back. This oscillation may persist for hours. The amplitude is usually small, often only a few centimetres of water level change, but it can produce alternating currents along the lagoon's length. Because the surface remains relatively flat, these alternating flows are difficult to detect visually. Channels within lagoons concentrate flow similarly to inlets. Natural depressions, dredge navigation paths, or scoured areas become preferred routes for water movement. Fish often follow these channels because food concentrates there. Swimmers drifting into them may experience stronger current than in surrounding shallow flats. The transition can be abrupt. One step may be in still water, the next in a gentle but persistent sideways flow. Wind shifts complicate matters. If wind direction changes quickly, surface flow reverses. Subsurface return flow adjusts with a delay. During that adjustment, multidirectional currents can exist simultaneously. This does not create dramatic turbulence, but it produces unpredictable drift patterns. Small craft operators sometimes notice this as a subtle steering challenge rather than visible disturbance. Thermal convection can generate localized currents as well. Shallow lagoon water heated by sunlight may develop small convection cells. Warm water rises, cooler water sinks nearby. These movements are generally weak, but can influence plankton distribution and sediment suspension. They illustrate how energy moves even without obvious external forcing. Human structures influence hidden currents. Marinas, docks, breakwaters, and causeways alter natural circulation. Water moving past pilings accelerates slightly due to constriction. Boat traffic can induce localized flow through propeller wash. Dredge channels create depth contrast that guide current paths. These effects are rarely dramatic individually, but combined they shape everyday lagoon circulation. Navigation charts often mark current-prone areas, especially near inlets. Mariners respect these because strong tidal streams can affect steering. Recreational swimmers rarely consult such charts. The absence of waves leads to the assumption that current hazards are minimal. In reality, many lagoon incidents involve slow drift rather than sudden pull. A swimmer may not feel alarm until distance from shore increases enough to require sustained effort to return. Biological indicators sometimes reveal hidden currents. Floating algae lines, foam streaks, or debris trails show flow direction. Fish schools often orient themselves relative to current for feeding efficiency. Observing these cues can provide insight, but they require attention that casual recreation may not encourage. Tidal timing remains critical. Near slack tide, when water level difference between lagoon and ocean is minimal, currents weaken. As the tide turns, gradients increase and flow strengthens. Local knowledge often includes safe crossing times for channels based on slack tide. Visitors without this information may enter water during peak exchange periods. Weather systems interacting with lagoons can produce pressure-driven currents. A passing low-pressure system raises sea level slightly offshore. If the lagoon responds more slowly due to restricted inlets, temporary gradients form. Water flows until equilibrium returns. These effects are subtle but measurable and can influence navigation and swimming conditions. Currents influence water quality distribution. Nutrients carried by runoff may accumulate in downcurrent areas. Oxygen-rich ocean water entering through passes may improve conditions locally. Pollutants can concentrate where circulation is weak. Understanding these patterns helps explain why some lagoon sections appear clearer or more biologically active than others. Visibility alone does not indicate safety. Clear water may have strong current. Turbid water may be nearly still. Depth is not always predictive either. Shallow flats can have steady lateral flow if wind pushes surface water consistently. Deeper channels may have stronger currents due to tidal exchange. Fatigue plays a role in hidden current risk. A current of only half a knot may not feel strong initially. Over time, maintaining position against it requires energy. Swimmers focusing on recreation rather than navigation may underestimate cumulative effort. Recognizing early drift allows easier correction than attempting return after significant displacement. Sound does not always reveal current strength. Unlike breaking waves, horizontal flow produces little noise unless interacting with structures or surface roughness. Silence reinforces the illusion of stillness. Only tactile sensation indicates movement, and that sensation may be subtle until speed increases. Technological tools can help detect hidden currents. Drifting buoys, GPS tracking, and current meters provide objective data. These tools show that even calm lagoons exhibit complex flow patterns. For everyday recreation, simpler observation techniques, such as watching floating markers or noting shoreline alignment changes, can offer clues. The existence of hidden currents underscores the difference between appearance and process. A lagoon's smooth surface reflects reduced wave energy, not absence of motion. Movement continues because water must respond to gravity, wind, temperature, salinity, and basin geometry. The barrier that created calmness also created confinement, and confinement shapes how energy moves. Understanding subsurface currents prepares the way for examining another phenomenon that often surprises people inside sheltered waters. Rip-like flows that resemble ocean rip currents, but occur in environments where waves are minimal. A rip current is usually associated with surf beaches. The typical image involves breaking waves, white foam, and a narrow channel of water rushing back out toward the sea. People expect them where waves are strong. That expectation creates a blind spot when similar outward flowing currents develop in lagoons. Without large breaking waves, these currents look different. They are quieter, often invisible from the surface, yet they still move water with enough persistence to carry swimmers away from where they started. Inside a lagoon, outward flowing currents most often form near openings in the barrier. When tide rises outside the lagoon, water flows inward through passes, channels, or breaches in sandbars. When tide falls, that water must leave. The outflow concentrates in the same narrow pathways. Because there are no large waves collapsing over those pathways inside the lagoon, the returning water does not produce the classic foamy streak associated with ocean rip currents. It simply flows outward, steady and directional. This outward flow can feel confusing rather than alarming. Instead of the sudden pull sometimes reported in surf zones, lagoon rip-like currents often feel like slow sideways drift that gradually becomes more noticeable. A swimmer may first assume wind is responsible. Only later, when effort to return increases, does the realization come that water movement is stronger than expected. One reason these disguised rip currents form is water level difference. If the ocean level drops faster than the lagoon level during a falling tide, gravity drives water outward. The narrower the channel, the faster the flow. This is basic continuity in fluid motion. Large volume through small space means increased velocity. The lagoon may still appear flat, but the channel becomes a conveyor belt of water moving seaward. Wind reinforces this effect. Persistent wind blowing toward the barrier pushes surface water against it. If the only exit is a pass or channel, the combined effect of wind setup and falling tide can strengthen outward flow. Because the surface inside the lagoon remains mostly unbroken, visual cues are minimal. Foam lines may not develop. Colour differences may be subtle. Sediment patterns sometimes reveal these flows. A narrow streak of slightly cloudier water extending from a pass toward open sea may indicate suspended sediment carried outward. However, lighting conditions, water clarity, and viewing angle affect visibility. Many people simply do not notice. Barrier reef lagoons provide clear examples. Reef passes are natural gaps where water exchange occurs. Divers often time entry based on tidal stage because currents through passes can be strong. From the lagoon side, the pass may look calm compared to the wave energy on the reef crest. Yet water can move steadily outward during ebb tide. Swimmers drifting too close to the pass may find themselves carried toward deeper water beyond the reef. Sandbar lagoons show similar behaviour. Storm events sometimes cut temporary channels through barrier islands. Even after waves subside, these channels remain pathways for tidal exchange. Because they may be new, signage or local awareness may lag behind. Visitors see a quiet inlet and assume stability. Underneath, water continues adjusting levels between lagoon and ocean. Human-made channels amplify the effect. Dredged cuts for boat access often provide deeper pathways than natural shallows. Water preferentially flows through deeper areas because resistance is lower. During tidal transitions, these dredged channels can host stronger currents than surrounding flats. Boaters recognise this through steering corrections. Swimmers may not anticipate it. The absence of breaking waves changes body feedback. In surf rips, waves push swimmers shoreward between pulses of seaward flow. That alternating force provides orientation cues. In lagoon, rip-like currents, pushback from waves is minimal. Movement is more constant. Without periodic shoreward push, drift may go unnoticed longer. Visibility plays a role again. Clear water may allow swimmers to see the bottom, giving confidence. If the bottom slopes gradually toward a channel, depth change may not signal increased current. The brain associates shallow visibility with safety, even when horizontal flow increases. Group dynamics influence response. If multiple swimmers drift together, each may assume the others are intentionally moving. Social cues override individual sensation. By the time someone suggests returning, the group may already be near the stronger part of the channel. Floating equipment changes perception too. Inflatable rafts, paddleboards and kayaks offer buoyancy, but also increase wind exposure. Wind pushing the craft toward a pass combined with tidal outflow can accelerate drift. Occupants may feel relaxed because they remain afloat, yet navigation back becomes more difficult. Temperature differences between lagoon and ocean sometimes mark these channels. Outflowing lagoon water may be warmer or less saline than ocean water. The mixing zone can produce slight surface texture differences, but these are subtle compared to surf foam. Experienced observers may notice a faint boundary line. Casual swimmers often do not. Biological indicators occasionally help. Fish feeding behaviour sometimes concentrates near passes because nutrient flow increases there. Bird activity may cluster as well. While interesting ecologically, these cues are not widely recognised as current indicators. Timing awareness reduces risk. Slack tide periods, when water level difference between lagoon and ocean is minimal, produce weaker currents. Entering water near passes during these times lowers drift potential. However, tide schedules vary regionally, and understanding them requires attention many recreational users do not give. Education campaigns about rip currents usually focus on surf beaches. Messaging often includes advice such as swim parallel to shore to escape a rip. In lagoons, orientation may differ because the channel may not align perpendicular to shoreline. Escaping may involve moving laterally relative to channel flow, not necessarily parallel to visible shore. Fatigue remains a central factor. A current that feels manageable for a short time can become exhausting if sustained. Warm lagoon water reduces initial perception of strain. By the time fatigue sets in, returning against current may require assistance. Technology provides insight. GPS drift tracking during tidal cycles shows clear outward movement through lagoon passes even under calm surface conditions. Such data confirm what local mariners often know intuitively. Calm appearance does not equal stagnant water. Infrastructure sometimes unintentionally encourages entry near passes. Docks, scenic viewpoints, or snorkeling attractions often cluster where water exchange improves clarity. Improved clarity attracts swimmers. The same exchange improves current strength. This overlap increases exposure. Weather variability matters. After storms, channels may deepen temporarily, increasing flow. Sediment later refills them partially. These changes alter current patterns over weeks or months. Static assumptions about safe areas may become outdated. Understanding rip currents in disguise requires shifting focus from wave observation to water level differences and channel geometry. The absence of foam does not eliminate directional flow. Instead, it masks it. Recognizing these currents leads naturally into another aspect of lagoon behavior. How limited circulation can cause water layers to form and persist, creating conditions very different from open ocean mixing. When water looks calm, people often assume it is also well mixed. That assumption comes from everyday experiences with small bodies of water where stirring quickly distributes temperature and particles evenly. Lagoons behave differently because their connection to the open ocean is restricted. Limited exchange means that once water enters, it may remain for extended periods. Movement continues, but circulation can be slow enough that layering develops. That layering, called stratification, creates zones with distinct temperature, salinity, oxygen content, and biological activity. Stagnation does not mean absolute stillness. It means circulation is insufficient to refresh the entire water body quickly. Imagine water entering through an inlet during rising tide. Some of it mixes immediately, but some remains in pockets, especially in corners of the basin or shallow flats shielded from prevailing wind. If tidal range is small or inlet geometry restricts flow, those pockets may retain water for days or weeks. During that time, chemical and biological processes continue inside them. Temperature differences are one of the main drivers of stratification. Shallow lagoon water warms quickly under sunlight. Warm water is less dense than cooler water. If cooler ocean water enters through an inlet at depth, it may slide beneath the warmer surface layer rather than mixing fully. The result is a two-layer system, warm water above, cooler water below. Without strong wind or tidal mixing, this layering can persist. Salinity differences create similar layering. Fresh water from rainfall, rivers, or groundwater inflow is less dense than seawater. After heavy rain, A thin layer of fresher water can spread across the lagoon surface. Beneath it, saltier water remains. This difference may be only a few parts per thousand, yet it is enough to maintain separation under calm conditions. The surface may appear uniform while density boundaries exist below. Oxygen distribution follows these layers. Surface water in contact with air usually contains higher dissolved oxygen. Photosynthesis by algae and seagrass adds more oxygen during daylight. In deeper layers, especially where organic material accumulates, decomposition consumes oxygen. If mixing is weak, bottom water can become oxygen poor. Fish and invertebrates sensitive to low oxygen may avoid those zones or experience stress. Stratification affects visibility as well. Suspended particles may accumulate at density boundaries. Divers sometimes notice a hazy layer separating clearer water above from darker water below. From the surface, this boundary is not visible. Swimmers may remain unaware that distinct environmental conditions exist beneath them. Wind plays a complex role. Moderate wind can mix surface layers, reducing stratification. Strong, persistent wind, however, can push warm surface water toward one side of the lagoon, allowing cooler, deeper water to upwell elsewhere. This redistribution changes local conditions quickly. Areas that felt comfortably warm may cool suddenly, while others warm further. Seasonal patterns influence stagnation. In warm climates, summer months often produce stronger stratification because heating is continuous and rainfall patterns vary. In temperate regions, seasonal temperature changes can create cycles of mixing and stratification. Cooler seasons promote mixing as surface water cools and sinks. Warmer seasons promote layering. Biological consequences of stagnation can be significant. Nutrients from runoff, sewage, or natural sources may accumulate. These nutrients encourage algae growth. Some algae species thrive in warm, nutrient-rich, low circulation environments. Blooms may appear as discoloration, surface scums, or invisible microscopic increases detectable only through testing. When algae die, decomposition consumes oxygen, intensifying low oxygen conditions in deeper layers. Fish behavior responds to these conditions. Species that require high oxygen may cluster near inlets where fresh ocean water enters. Others tolerant of lower oxygen may remain in interior areas. Sudden mixing events such as storms can redistribute low oxygen water upward, stressing marine life quickly. Observers sometimes notice fish gasping near the surface after such events. Stagnation also influences microbial growth. Warm, nutrient-rich water with limited circulation supports bacteria populations. Most are harmless, but some can affect human health through skin irritation or ingestion. Water quality monitoring often increases in lagoons used for recreation because conditions favour microbial persistence. Sediment interactions add another dimension. Organic matter settling on the lagoon floor decomposes slowly. This process releases nutrients back into the water. If circulation is weak, these nutrients remain local, reinforcing cycles of productivity and decay. Soft sediments can trap gases produced during decomposition, such as methane or hydrogen sulfide. When disturbed by storms or human activity, these gases may escape, occasionally producing noticeable odours. Human development intensifies stagnation risks. Coastal construction sometimes reduces natural water exchange by narrowing inlets or altering shoreline contours. Stormwater runoff introduces additional nutrients. Boat traffic can resuspend sediments, increasing turbidity. Without careful management, these factors combine to reduce water quality. Infrastructure designed for recreation sometimes unintentionally promotes stratification. Floating docks shade water, reducing local photosynthesis. Artificial basins with limited openings can create microenvironments within the lagoon where circulation is even weaker. These areas may experience faster temperature increase and oxygen depletion. Monitoring programs often measure temperature and salinity profiles vertically to assess stratification strength. Instruments lowered through the water column record gradual or abrupt changes. These data help predict biological responses and inform management decisions. For the casual observer, however, such layering remains invisible. The sensation of entering stratified water can be noticeable. Swimmers sometimes feel sudden temperature change at a certain depth. That change marks a density boundary. While not inherently dangerous, it signals limited mixing. Awareness of such boundaries can inform expectations about oxygen levels and biological activity below. Stagnation influences odour as well. Certain lagoons develop mild, sulphur-like smells in low oxygen zones. This is a byproduct of anaerobic bacterial activity. The presence of such odour indicates reduced mixing and altered chemical conditions. While not always harmful, it reflects environmental stress. Tidal flushing counteracts stagnation when inlets are sufficiently large. Regions with strong tidal range often experience better mixing. Conversely, lagoons with minimal tidal variation rely more on wind for circulation. Calm weather periods therefore increase stagnation potential. Climate change considerations are increasingly relevant. Rising temperatures promote stronger stratification by warming surface layers more rapidly. Sea level rise can alter inlet geometry, affecting flushing rates. Increased rainfall variability can intensify freshwater layering events. These changes modify lagoon dynamics over long time scales. Public perception rarely includes these subtleties. Calm surface equals safe water remains a common assumption, yet calmness can coincide with reduced oxygen, altered chemistry, and concentrated biological activity. Understanding stagnation reframes calm water as a dynamic environment rather than a static one. Navigation implications exist too. In stratified lagoons, boat wakes may mix layers locally. This mixing can temporarily improve oxygen distribution, but also resuspend sediments. Small craft operators may notice changes in water clarity after heavy traffic, even when wind is light. Ecological resilience depends partly on maintaining adequate circulation. Restoration projects sometimes focus on reopening blocked channels or enhancing tidal exchange. These interventions aim to reduce stagnation and improve water quality, while preserving the protective function of barriers. The existence of stratified, slowly circulating water explains why certain lagoon environments can experience rapid ecological shifts. A sudden storm mixing layers, a heat wave intensifying surface warming, or a pollution event adding nutrients can alter conditions quickly. The confined nature of lagoons amplifies responses compared to open ocean systems. Understanding stagnation and stratification leads directly into another critical consequence. When oxygen levels drop significantly, both marine life and human interaction with the water can be affected in ways that are not always immediately visible. When water circulation slows enough, oxygen distribution begins to change. Oxygen enters water mainly through two processes: direct exchange with the atmosphere at the surface and photosynthesis by aquatic plants and algae. In open ocean conditions, constant mixing distributes that oxygen throughout the water column. In lagoons, restricted circulation means oxygen added at the surface may not reach deeper layers efficiently. At the same time, biological processes continue consuming oxygen below. The idea that water contains oxygen is not always intuitive because oxygen is invisible. Yet aquatic organisms rely on dissolved oxygen just as land organisms rely on oxygen in air. Fish extract it through gills. Microorganisms use it for metabolism. When levels drop, stress begins. The process is gradual at first. Small declines may not produce obvious signs. Over time, however, depletion can become significant. Low oxygen conditions, often called hypoxia, develop when consumption outpaces replenishment. Organic material plays a major role. Leaves, algae, plankton, and waste entering a lagoon eventually settle and decompose. Decomposition is carried out by bacteria that consume oxygen as they break down organic matter. In a well-mixed system, New oxygen replaces what is used. In a stagnant lagoon, replacement may be slow. Temperature intensifies the issue. Warm water holds less dissolved oxygen than cold water. Because lagoons are shallow and often warm, they start with lower oxygen capacity. When heating continues during calm weather, oxygen solubility decreases further. Meanwhile, metabolic rates of organisms increase with temperature, meaning oxygen consumption accelerates. This combination pushes conditions toward depletion. Stratification compounds the problem. If warmer, lighter water sits above cooler, denser water, mixing is limited. Surface oxygen does not easily reach the bottom. Bottom layers may gradually lose oxygen entirely. These zones are sometimes called anoxic when oxygen approaches zero. Anoxic conditions change chemical reactions. Certain bacteria begin producing hydrogen sulfide, a gas recognizable by a sulfur-like odor. Fish and invertebrates respond behaviorally before conditions become lethal. Many species move toward the surface where oxygen is higher. Observers sometimes notice fish gathering near the air-water interface or near inlets where fresh ocean water enters. This behavior signals stress even if the water still looks clear. Large-scale fish mortality events occasionally occur in lagoons following sudden oxygen depletion. These events often happen after algal blooms collapse. While algae grow, they may produce oxygen during daylight. When they die, decomposition consumes oxygen rapidly. If circulation is limited, the system cannot compensate quickly. Fish kills can occur overnight under certain conditions. Human perception of low oxygen water is limited. Unlike murky water or visible debris, oxygen concentration does not change appearance directly. A lagoon may look inviting while deeper layers are oxygen poor. Swimmers generally remain in surface layers where oxygen exchange with air occurs, but divers or those wading deeper channels may encounter water with different chemical characteristics. Low oxygen influences more than fish survival. It affects overall water quality. Certain chemical compounds behave differently in oxygen-poor environments. Nutrients bound in sediments may be released, fueling further algal growth. Metals may change oxidation state, altering toxicity. These chemical feedback loops can prolong poor conditions even after initial causes subside. Urban runoff contributes significantly in developed coastal areas. Fertilizers, sewage, and organic waste increase nutrient levels. More nutrients encourage more biological production. More production eventually leads to more decomposition. Without adequate flushing, oxygen demand remains elevated. Monitoring programs in many regions track nutrient input precisely because of this connection. Mangrove-lined lagoons illustrate both resilience and vulnerability. Mangroves trap sediment and filter nutrients, helping maintain balance. However, if water exchange is restricted further by human alteration, even mangrove systems can experience oxygen stress. Restoration projects sometimes reopen tidal creeks specifically to improve oxygen distribution. Oxygen depletion also affects microbial populations directly relevant to human health. Some bacteria thrive in low oxygen environments. While not all are harmful, conditions that support their growth may coincide with increased pathogen persistence. Public health advisories sometimes restrict swimming when oxygen levels drop or when related water quality indicators exceed safe thresholds. Divers occasionally report encountering thermoclines or haloclines accompanied by low oxygen. A thermocline marks temperature change. A halocline marks salinity change. When these coincide with low oxygen, divers may notice reduced visibility, unusual odours, or changes in marine life behaviour. Such conditions usually remain localised, but illustrate how layered water can differ significantly within short vertical distances. Navigation and boating are indirectly affected. Oxygen-poor bottom water may accumulate organic gases that escape when sediments are disturbed by propellers. While rarely dangerous, these releases can alter water clarity and smell. They also indicate limited mixing. Seasonal cycles influence oxygen dynamics. During calm summer months, stagnation and warming increase depletion risk. Cooler seasons often restore mixing through temperature changes and storms. Understanding these cycles helps coastal managers anticipate periods of vulnerability. Weather events can abruptly change oxygen conditions. Strong winds mix water layers, sometimes improving oxygen distribution. However, if bottom water is severely depleted, mixing may bring low oxygen water upward suddenly. Fish adapted to surface conditions may experience stress quickly. Such events highlight how dynamic lagoon systems can be despite outward calm. Climate trends suggest increasing attention to oxygen. Dynamics will be necessary. Rising global temperatures favour stronger stratification. Increased coastal development adds nutrient sources. Sea level changes alter flushing efficiency. These combined factors influence how often low oxygen conditions occur. Public awareness remains limited because low oxygen lacks dramatic visual cues. Education efforts often focus on visible hazards like storms or waves. Communicating invisible chemical changes requires explanation rather than spectacle. Yet understanding these processes helps explain why some lagoons periodically experience ecological stress. From a safety perspective, swimmers rarely face direct danger from low oxygen in surface water. The primary concern lies in ecosystem health, water quality, and indirect effects such as increased microbial growth. Awareness helps individuals make informed choices about entering water after events like heavy rainfall, algal blooms, or fish mortality incidents. Research continues on improving lagoon resilience. Techniques include enhancing tidal exchange, reducing nutrient input, restoring vegetation, and monitoring water chemistry. These measures aim to maintain adequate oxygen levels while preserving the ecological and recreational value of lagoons. Understanding oxygen depletion connects naturally to another phenomenon common in enclosed warm waters: the development of toxic biological blooms that thrive under nutrient-rich, low circulation conditions. When water circulation slows and nutrients accumulate, biological growth often follows. In lagoons, this growth can become unusually concentrated because boundaries limit dispersal. One of the most significant consequences of this concentration is the development of harmful algal blooms, often called toxic blooms. These blooms occur when microscopic algae, cyanobacteria, or other plankton multiply rapidly under favourable conditions. The water may still look calm, warm and sheltered, yet its chemistry and biological activity can change in ways that affect wildlife, human health, and overall ecosystem stability. Algae are not inherently dangerous. They form the base of aquatic food webs. They produce oxygen during photosynthesis and support fish, crustaceans, and larger marine animals. Problems arise when specific species grow excessively. Lagoons provide several factors that encourage this growth. Shallow depth allows sunlight to penetrate easily. Warm temperatures accelerate metabolic rates. Nutrients from runoff, sewage, agricultural fertilizers, or natural organic material remain longer because flushing is limited. Together, these factors create an environment where certain algae reproduce faster than normal ecological balance would allow. Some blooms are visible immediately. Water may turn green, brown, red, or even milky depending on species involved. Surface scums can form in still conditions, especially along shorelines where wind pushes floating cells together. Other blooms remain invisible. The water may look clear, yet toxin-producing microorganisms may be present in high concentrations. Laboratory testing is often required to detect them. Toxins produced by certain algae serve biological purposes, often deterring grazing by other organisms. For humans and larger animals, these toxins can cause irritation, illness, or in extreme cases more serious health effects. Exposure routes vary. Skin contact during swimming can produce rashes or irritation. Inhalation of aerosolized toxins from wave splash or wind-blown droplets can affect respiratory comfort. Ingestion through contaminated seafood or water is another pathway, though seafood safety monitoring programs often reduce this risk. Enclosed lagoons amplify bloom persistence. In open ocean settings, currents and wave action disperse algae populations over wider areas. Concentrations may still occur but often fluctuate quickly. In lagoons, reduced circulation allows blooms to remain localized and dense. Even after initial growth slows, cells may remain trapped behind barriers. Wind shifts can redistribute them within the lagoon rather than dispersing them offshore. Temperature plays a consistent role. Warm water promotes faster reproduction of many algae species. Because lagoons warm quickly and retain heat longer than adjacent ocean waters, they often reach temperatures favourable for bloom formation earlier in the season. Extended calm weather periods intensify this effect by reducing mixing and maintaining stable warm surface layers. Nutrient input is another critical factor. Nitrogen and phosphorus compounds from fertilizers, wastewater, storm runoff, or decomposing organic matter provide fuel for algal growth. In urbanized coastal areas, even small nutrient increases can shift ecological balance. Without strong flushing, these nutrients accumulate. Monitoring programs frequently measure nutrient levels precisely because of their connection to bloom risk. Rainfall patterns influence timing. Heavy rains wash nutrients from land into lagoons. The immediate effect may be turbidity and freshwater layering. Within days or weeks, algae populations may respond to increased nutrient availability. Calm weather following rainfall often correlates with bloom development. Salinity variability affects species composition. Some toxin-producing cyanobacteria tolerate brackish conditions well. Lagoons with fluctuating salinity due to rainfall, evaporation or freshwater inflow provide suitable habitat for these organisms. This flexibility allows blooms to occur across a wide range of lagoon types. Light availability remains essential. Because lagoons are shallow, sunlight often reaches the bottom, encouraging not only free-floating algae but also benthic microalgae attached to sediments or vegetation. These benthic communities can release toxins into surrounding water when disturbed by wind, waves or human activity such as boating. Biological feedback loops complicate matters. As algae grow, they shade deeper water, reducing photosynthesis by other plants like seagrass. Reduced seagrass health decreases oxygen production and sediment stabilization. Sediments then release additional nutrients, further supporting algae growth. This cycle can continue until environmental conditions shift. Wildlife impacts vary. Fish may experience gill irritation or oxygen stress when blooms decompose. Shellfish can accumulate toxins without appearing unhealthy, which is why shellfish harvesting regulations often respond quickly to bloom reports. Birds feeding on contaminated prey may experience secondary exposure. Human recreation intersects with bloom timing frequently, because warm, calm weather encourages both swimming and algae growth. People entering water during early bloom stages may notice only slight discoloration or unusual odour. Later stages may produce more visible signs, but by then toxin levels may already have been present for some time. Odour sometimes accompanies blooms. Certain species produce compounds with earthy, musty or sulphur-like smells. Odour alone does not confirm toxicity, but it signals biological activity worth noting. Coastal managers often treat persistent, unusual odours as indicators requiring further investigation. Water clarity changes as well. Blooms scatter light, reducing transparency. Reduced visibility affects not only aesthetics but also safety. Swimmers may have difficulty judging depth or spotting underwater hazards. Divers may avoid areas with poor clarity, but casual swimmers may not anticipate reduced visibility effects. Public communication about blooms varies by region. Some areas maintain active monitoring programs with regular advisories. Others rely on reactive reporting after visible blooms appear. Differences in monitoring resources influence public awareness. Education campaigns emphasize avoiding contact with discoloured water, but invisible blooms remain challenging to communicate. Technological monitoring has improved detection. Satellite imagery can identify large-scale discoloration. Automated sensors measure chlorophyll concentration, temperature, salinity, and oxygen levels. Laboratory analysis confirms toxin presence. These tools allow earlier warnings than visual observation alone. Climate variability influences bloom frequency. Warmer average temperatures, altered rainfall patterns, and changing nutrient runoff all affect lagoon conditions. Many regions report increasing bloom occurrences over recent decades. Research continues on distinguishing natural variability from human-driven trends. Management responses include reducing nutrient input, improving wastewater treatment, restoring wetlands that filter runoff, and enhancing tidal exchange where feasible. These measures aim to address root causes rather than symptoms. Short-term responses sometimes involve temporary swimming advisories or shellfish harvesting closures. Economic implications extend beyond health concerns. Tourism may decline during visible bloom events. Fisheries may experience temporary closures. Waterfront property values can fluctuate based on perceived water quality. These economic effects motivate investment in monitoring and mitigation. Cultural perception of lagoons as calm recreational spaces sometimes delays recognition of bloom risk. People accustomed to associating danger with rough seas may overlook chemical hazards in still water. Effective communication emphasizes that calm appearance does not guarantee safe water chemistry. Medical research continues on toxin effects. Most exposures produce mild symptoms, but certain toxins can affect liver or nervous system function under significant exposure. Public health agencies track incidents and refine guidance accordingly. Prompt reporting helps refine understanding. Environmental recovery from blooms varies. Some dissipate quickly once conditions change. Others persist until strong flushing or temperature shifts occur. Sediment nutrient stores can prolong recovery even after visible algae decline. Long-term management focuses on preventing recurrence rather than relying solely on natural dispersal. Wildlife adaptation also occurs. Some species tolerate blooms better than others. Shifts in species composition may follow repeated bloom events. These ecological changes influence fishing patterns and biodiversity. Educational outreach increasingly emphasizes personal observation. Recognizing unusual water color, persistent scums, dead fish presence, or strong odors encourages cautious behavior. Simple avoidance until conditions clarify often prevents exposure. The presence of toxic blooms highlights how biological processes respond to physical confinement. The same sheltered conditions that make lagoons attractive for recreation can encourage biological activity that requires monitoring. Calm water supports growth. Limited exchange sustains it. This biological dimension connects closely with chemical variability in lagoons. Changes in salinity, temperature, and nutrient concentration influence bloom formation and persistence. Understanding these chemical shifts helps explain why conditions can change quickly even when surface appearance remains stable. Salinity sounds like a simple concept at first. It refers to the amount of dissolved salts in water, usually measured in parts per thousand. The open ocean tends to stay within a relatively stable range, typically around 35 parts per thousand. That stability exists because of constant large-scale mixing. Lagoons rarely have that level of consistency. Their semi-enclosed nature allows salinity to change more quickly, sometimes within hours, and those changes affect everything from water density to marine life behavior and human comfort in the water. The most obvious factor influencing lagoon salinity is freshwater input. Rainfall, rivers, groundwater seepage, and surface runoff all introduce water with lower salt concentration. After heavy rain, especially in tropical or coastal storm conditions, a lagoon can develop a fresher surface layer. Because fresh water is less dense than seawater, it tends to spread across the top rather than mix immediately. From above, the water may still appear clear and inviting, yet chemically it has shifted. Evaporation works in the opposite direction. In hot climates with limited freshwater inflow, lagoons can become more saline than the adjacent ocean. Water evaporates, leaving salts behind. This process concentrates salinity over time. Shallow lagoons are particularly susceptible because their large surface area relative to volume accelerates evaporation. During prolonged dry spells, salinity can climb noticeably, sometimes enough to stress marine organisms adapted to narrower ranges. Tidal exchange moderates these swings, but the effectiveness depends on inlet size and frequency of tidal flushing. A lagoon with wide deep channels exchanges water more easily, stabilizing salinity. A lagoon with narrow or shallow inlets retains fresh water or concentrated salt water longer. Timing matters too. If rainfall coincides with neap tides, when tidal range is smaller, flushing may be minimal. If rainfall coincides with spring tides, stronger exchange may restore balance faster. Wind also influences salinity distribution. Persistent wind pushes surface water toward one side of the lagoon. If that surface layer is fresher due to rain, it accumulates downwind. Meanwhile, saltier water may move beneath toward the upwind side. This redistribution creates spatial variability. One shoreline may have noticeably fresher water than another, even within the same lagoon. Temperature interacts with salinity through density effects. Warm, fresh water is particularly light compared to cooler, saltier water. This combination enhances stratification. Layers resist mixing until wind, tidal flow, or cooling events disrupt them. Such disruptions can cause sudden chemistry changes as previously separated layers mix. Marine organisms respond quickly to salinity fluctuations. Some species tolerate wide ranges, others require stable conditions. Fish, crustaceans, and mollusks may migrate toward areas where salinity suits them best. Sudden shifts can cause stress, reduced feeding, or relocation. Aquaculture operations monitor salinity closely because even moderate changes affect growth and health. Human swimmers may notice salinity changes physically. Saltier water increases buoyancy slightly. Fresher water reduces it. The difference is subtle, but detectable over time. Skin and eye comfort also vary. Highly saline lagoon water can cause more irritation than typical ocean water. Conversely, fresher lagoon water may feel softer, but could carry increased runoff contaminants after rain. Chemical reactions in lagoon water depend on salinity. Nutrient availability, metal solubility, and biological uptake rates all shift with salt concentration. For example, certain algae species flourish in brackish conditions. Others prefer fully marine salinity. Sudden shifts can favor different species, sometimes triggering ecological imbalances. Water clarity may change with salinity as well. Freshwater runoff often carries sediments, organic matter, and pollutants. After rainfall, turbidity may increase, reducing visibility. Over time, sediments settle, but chemical residues may remain. Monitoring programs often increase sampling frequency after major rainfall for this reason. Groundwater interactions complicate the picture. In some coastal regions, freshwater aquifers discharge into lagoons beneath the surface. These inputs are not always visible. They can create localized pockets of fresher water even without rainfall. Conversely, seawater intrusion into aquifers during droughts can alter lagoon chemistry indirectly. Storm surges add another dimension. High sea levels during storms push saltier ocean water into lagoons. If barriers prevent rapid drainage afterward, elevated salinity may persist. Combined with debris and nutrient influx from land, this can create complex chemical environments requiring time to stabilize. Pollutant behavior depends partly on salinity. Some contaminants bind to particles differently in fresh versus salt water. Changes in salinity can release previously settled pollutants back into the water column. This process is not always visible but affects water quality. Aquatic vegetation reflects salinity conditions. Seagrass species differ in tolerance. Sudden shifts may stress them, reducing coverage. Reduced vegetation affects sediment stability and habitat availability for fish. Mangroves also respond to salinity changes, with some species thriving in brackish conditions while others require more stable marine salinity. Temperature fluctuations compound chemical effects. Warm water accelerates chemical reactions. A lagoon experiencing both salinity change and warming may see faster ecological responses than either factor alone would produce. Human infrastructure sometimes influences salinity intentionally. Flood control gates, navigation locks, or managed inlets can regulate water exchange. These interventions aim to balance ecological health with human needs. Improper management, however, may unintentionally increase variability. Monitoring technology helps track salinity in real time. Sensors deployed in lagoons measure conductivity, temperature, and depth continuously. Data from these sensors inform management decisions such as opening inlets, issuing advisories, or adjusting aquaculture practices. Cultural knowledge often complements technology. Long-time residents may recognize patterns tied to seasonal rainfall, wind direction, or tidal cycles. Such observational knowledge can provide early warning of salinity shifts before formal measurements confirm them. Climate trends suggest increasing variability in precipitation and temperature. These trends may intensify salinity swings in many lagoon systems. Coastal planners consider these factors when designing infrastructure or conservation strategies. Education about salinity tends to focus on ecology rather than recreation, yet recreational safety intersects with chemistry. Freshwater runoff may introduce pathogens. High salinity may concentrate irritants. Awareness of recent weather and water conditions helps inform decisions about entering lagoon water. Fishery management also depends on salinity understanding. Certain species spawn only within specific ranges. Sudden changes can affect catch patterns. Fisheries often adjust practices accordingly. Public health advisories sometimes reference salinity indirectly through water quality indicators. After major rain events, advisories may recommend avoiding swimming due to runoff effects. Understanding salinity helps explain the reasoning behind such guidance. Visual cues for salinity change are limited. Slight colour differences, floating debris lines, or plant stress may hint at shifts, but measurement remains the most reliable method. This invisibility reinforces the need for awareness rather than reliance on appearance. The chemistry of lagoons remains dynamic because of their transitional nature between land and sea. That dynamism contributes to ecological richness but also to unpredictability. Recognizing salinity swings provides insight into why lagoon environments can change quickly despite calm surfaces. Chemical variability connects directly to biological presence. Certain wildlife species prefer these shifting conditions, using lagoons as feeding, breeding, or resting grounds. Understanding how animals respond to these chemical shifts helps explain another dimension of lagoon safety. Lagoons often look inviting precisely because they appear sheltered. The absence of heavy surf suggests fewer large marine predators, fewer dramatic encounters, and fewer visible threats. That perception contains some truth. Many large pelagic species prefer deeper offshore waters. However, lagoons are not empty. They are biologically active transition zones where fresh water, seawater, sediment, sunlight, and nutrients combine. These conditions support a wide range of organisms, some of which are adapted specifically to calm, shallow, and enclosed environments. One of the most important ecological roles of lagoons is serving as nursery habitat. Juvenile fish of many species use lagoons for protection from open ocean predators. Shallow depth and vegetation such as seagrass or mangrove roots provide shelter. While this nursery function benefits fish populations, it also means lagoons can contain high densities of young marine life. In most cases, this is harmless to swimmers, but it establishes the principle that sheltered water supports concentrated wildlife activity. Stingrays are common inhabitants of sandy lagoon bottoms. They often bury themselves beneath a thin layer of sand with only their eyes visible. In shallow, clear water, they are sometimes visible, but turbidity or glare can conceal them. A startled stingray may use its tail defensively if stepped on. The risk can be reduced by shuffling feet when walking in shallow areas, which alerts the animal and gives it time to move away. The presence of stingrays does not indicate aggression, but it does demonstrate how lagoon wildlife interacts closely with human recreation. Jellyfish frequently accumulate in lagoons because barriers reduce dispersal. In open ocean conditions, currents may carry jellyfish over large distances. Inside a lagoon, wind and tidal patterns may concentrate them along certain shorelines. Some species cause mild irritation, others can cause more significant stings. Calm water sometimes increases encounter likelihood because swimmers may not see translucent bodies drifting below the surface. Certain lagoons, particularly in tropical regions, host small sharks that use shallow water as nursery areas. These species are typically not interested in human interaction and often avoid contact. Nonetheless, their presence reflects the ecological function of lagoons as safe havens for early life stages. Awareness rather than alarm is appropriate, but recognition that wildlife density can be higher than expected is important. Brackish lagoons in some parts of the world support crocodiles or alligators. These reptiles prefer slow-moving water and may use lagoon edges or connected mangrove channels. Such environments are usually well known locally, and signage is common where large reptiles are present. The broader point is that lagoon conditions often favour species adapted to calm, warm, and sheltered water. Bird life thrives around lagoons. Wading birds feed on fish and invertebrates in shallow flats. While birds themselves pose little risk, their droppings contribute nutrients that can influence water chemistry. Concentrations of birds may correlate with areas of high biological productivity. Parasites and microorganisms also flourish in lagoon settings. Snails in some brackish lagoons host parasites that can cause skin irritation when larvae are released into the water. Most cases are mild and temporary, but they illustrate how biological interactions increase when circulation is limited. Mangrove ecosystems associated with lagoons host crabs, fish, and insects, adapted to fluctuating salinity and temperature. Mangrove roots trap organic material, creating nutrient-rich conditions. While these habitats are ecologically valuable, they also increase biological density near shorelines. Seagrass meadows stabilize sediment and provide habitat for many species. They also attract herbivorous fish and invertebrates. In clear lagoons, swimmers may enjoy observing this life. However, dense vegetation can entangle fishing lines or small boat propellers, affecting navigation. Mosquito populations may increase near stagnant lagoon edges, especially where freshwater inflow creates breeding conditions. While this is primarily a shoreline concern rather than a water safety issue, it reflects the broader ecological productivity of calm water. Marine snakes inhabit some tropical lagoons. Most are non-aggressive and avoid contact, but their presence underscores the diversity of species that use sheltered waters. Public education about local species reduces unnecessary fear while promoting informed behaviour. Crustaceans such as crabs and shrimp thrive in nutrient-rich shallow environments. Some burrow into sand or mud. Burrowing can destabilize sediment slightly, contributing to soft spots on lagoon floors. Swimmers stepping into soft sediment may experience unexpected sinking sensations, though rarely dangerous. Fish feeding behavior sometimes intensifies during certain tidal phases. As water flows through channels, small prey concentrate, attracting larger fish. These feeding aggregations may occur near inlets where currents are strongest. While typically harmless, increased activity can surprise swimmers unfamiliar with fish behavior. Seasonal migration patterns influence lagoon wildlife presence. Certain species enter lagoons only during breeding seasons. Others leave when salinity or temperature shifts beyond tolerance. These seasonal changes mean that lagoon wildlife composition varies throughout the year. Human feeding of wildlife alters natural behaviour. Fish accustomed to being fed near docks or marinas may associate swimmers with food sources, increasing proximity. Responsible practices discourage feeding to maintain natural behaviour patterns. Nighttime introduces different wildlife dynamics. Many species become more active after sunset. Reduced visibility increases encounter uncertainty. Swimmers and boaters may not see animals that would otherwise be visible in daylight. Disease transmission among wildlife sometimes increases in enclosed water. Higher density and limited circulation can facilitate pathogen spread among fish or invertebrates. While such outbreaks primarily affect marine life, they signal ecological imbalance. Aquaculture operations in lagoons introduce additional species. Farmed fish or shrimp may escape during storms, altering local ecosystems. Waste from aquaculture can increase nutrient levels, indirectly influencing wildlife patterns. Wildlife adaptation to human presence varies. In heavily used recreational lagoons, animals may avoid high-traffic areas during peak hours. In quieter sections, activity may remain high. Spatial variation within the same lagoon can therefore be significant. Environmental management often balances wildlife protection with human recreation. Protected zones may restrict access during breeding seasons. Such measures reflect the ecological importance of lagoons. Understanding wildlife presence reframes lagoons as active ecosystems rather than empty swimming spaces. Most wildlife interactions are neutral or positive, offering opportunities for observation and appreciation. However, awareness of species adapted to sheltered water conditions helps prevent accidental encounters. The concentration of wildlife links back to earlier themes: confinement, nutrient accumulation, and chemical variability. All contribute to ecological richness and complexity. This complexity also interacts with weather events, particularly storms, which can transform calm lagoon systems rapidly when energy from the open ocean becomes temporarily overwhelming. Storms change water behavior long before waves arrive. Atmospheric pressure drops, winds strengthen, and water begins to respond to those forces. In the open ocean, storm energy spreads over vast distances. Waves travel outward, currents redistribute water, and coastal impacts vary depending on geography. Lagoons respond differently because they are enclosed basins with limited outlets. The same barriers that soften everyday wave action can trap water during storms, allowing energy to accumulate instead of dissipating. A storm surge is essentially a rise in sea level caused primarily by strong winds, pushing water toward shore, combined with lower atmospheric pressure, allowing water to expand slightly upward. When that surge reaches a coastline with open exposure, waves break, water spreads laterally, and part of the energy disperses across wide areas. When the coastline includes lagoons behind reefs, barrier islands, or sandbars, water entering the lagoon can become confined. Entry points into lagoons are usually narrow compared with the basin behind them. During storm conditions, ocean water forced toward the coast finds those openings and flows inward. Because wave crests are already elevated by surge conditions, even modest overtopping of barriers can introduce additional water. Once inside, the lagoon's limited exit capacity slows the return flow. Water levels rise internally. This internal rise may not immediately look dramatic. There may be no crashing surf along lagoon shorelines, only gradual encroachment of water over low-lying land. People unfamiliar with storm behaviour sometimes interpret this slower rise as less dangerous. In reality, confined water can reach higher levels because it has fewer paths to escape. Flooding can therefore extend farther inland around lagoon margins than expected. Wind direction strongly influences how energy distributes. If wind blows consistently toward the barrier, water piles against it. In a lagoon, this can create a setup effect where one side experiences higher water levels than another. The difference may be small in absolute terms, but over large, shallow areas, even small increases can translate into widespread flooding. Storm timing relative to tidal cycles matters too. A storm surge arriving during high tide raises baseline water levels further. Lagoons with narrow inlets may already be near equilibrium with ocean tide. Additional surge water must accumulate internally before it can drain. This lag increases flood duration. Wave reflection inside lagoons becomes important during storms. While barriers reduce incoming wave height, some energy still enters as swell or overtopping. Inside the lagoon, waves reflect off shorelines, seawalls, docks, and natural slopes. Reflection can produce choppy conditions even without large surf. Boats moored in lagoons sometimes experience unexpected motion because reflected waves intersect. Sediment movement accelerates during storms. Fine sediments on lagoon bottoms can resuspend, reducing visibility and altering depth temporarily. Channels may deepen or shift slightly. Sandbars can migrate. After the storm, these changes affect circulation patterns. Areas previously shallow may become deeper and vice versa, influencing future water movement. Infrastructure around lagoons often assumes calmer baseline conditions. Marinas, homes, roads, and recreational facilities cluster along sheltered shores. During storm surge events, these areas may flood not from direct ocean wave impact, but from water trapped behind barriers. Drainage systems designed for normal tides may not cope with surge levels. Rainfall accompanying storms adds fresh water to the lagoon. Combined with ocean surge, this increases total water volume. Freshwater runoff may carry debris, nutrients, and pollutants into the basin. Water quality can deteriorate temporarily after storms, even when flooding subsides. Barrier stability is not guaranteed under extreme conditions. Sandbars may breach, creating temporary new inlets. Coral reef crests may experience damage. These structural changes alter future energy flow. A lagoon that once flushed slowly may gain a new channel, increasing exchange. Conversely, sediment deposition after a storm may narrow an existing inlet, reducing flushing. Communication about storm risk sometimes emphasizes open ocean exposure. Communities around lagoons may underestimate risk because they are shielded from direct surf. Historical flood records often reveal that lagoon-adjacent areas experience significant inundation during major storms. Awareness campaigns increasingly include lagoon-specific guidance. Boating safety during storms reflects these dynamics. Operators sometimes assume lagoons provide safe harbour. While wave heights may be reduced compared with open sea, rising water levels, strong currents near inlets, and debris movement still pose hazards. Securing vessels requires consideration of changing water height rather than wave action alone. Ecologically, storm surges redistribute nutrients and organisms. Fish may move into newly flooded areas temporarily. Vegetation may experience saltwater exposure beyond normal limits. Recovery periods vary depending on surge magnitude and duration. Water temperature and salinity often shift after storms. Surge water from the ocean may increase salinity temporarily, while rainfall reduces it. Mixing during storm turbulence may disrupt previous stratification, redistributing oxygen and nutrients. These chemical changes can influence post-storm biological activity. Human response planning increasingly integrates lagoon behaviour. Evacuation zones consider internal flooding potential. Urban planning evaluates drainage and barrier resilience. Restoration projects sometimes aim to improve natural buffering capacity without eliminating protective barriers entirely. Public perception continues to evolve. The absence of large waves inside lagoons can create false reassurance during storms. Education efforts emphasize that water level rise, not wave height alone, determines flood risk in enclosed basins. Technological forecasting tools now include high-resolution coastal models that simulate surge behavior in complex lagoon systems. These models incorporate wind, pressure, tide, and topography data to predict internal water level changes. Such forecasts help authorities issue timely warnings. Historical case studies illustrate variability. Some storms produce minimal lagoon flooding because wind direction favours offshore flow. Others, even with similar intensity, cause severe internal flooding because wind pushes water toward lagoon entrances. Local geography determines outcome. Climate projections suggest potential changes in storm patterns and sea level. Rising baseline sea level means smaller surges may produce effects previously associated with larger storms. Lagoon communities increasingly consider long-term adaptation strategies. Understanding how storms interact with lagoons clarifies why sheltered water does not guarantee safety. Barriers redirect energy rather than eliminating it. When external forces intensify, confinement can amplify water level changes and prolong flooding. Storm dynamics also interact with atmospheric conditions preceding major weather systems. Periods of unusual calm often occur before severe storms, creating a deceptive sense of stability. Recognizing that calmness can precede significant change helps explain why enclosed waters sometimes shift rapidly from tranquil to hazardous conditions. Before a cyclone, hurricane, or typhoon fully arrives, conditions along the coast often become unusually calm. Wind may drop, waves that normally break along reefs or barrier islands can flatten noticeably. The sky may look hazy or still rather than turbulent. In lagoons especially, this calm can feel reassuring. Water surfaces become glassy, boats drift quietly, shorelines seem protected. Yet this calm is not stability. It is a transitional phase created by shifting atmospheric pressure, changing wind direction, and the early influence of a large rotating storm system. Cyclones are organised systems driven by pressure gradients. At the centre, atmospheric pressure is lower than the surrounding environment. Air flows inward toward that centre. As the storm approaches, pressure differences begin influencing water levels even before strong winds reach a specific coastline. Lower pressure allows water to rise slightly because there is less downward atmospheric force on the ocean surface. This rise may be small initially, but it contributes to storm surge potential later. Wind behaviour during this phase is complex. Outer circulation bands may not yet affect a lagoon directly. Local winds may weaken or change direction temporarily. Without steady wind, surface water becomes smoother. Waves generated earlier dissipate. This reduction in surface disturbance can be misinterpreted as a sign that the storm will bypass the area or weaken. In reality, it often means the system is reorganizing energy. Inside lagoons, the effect is amplified. Barriers already reduce wave energy under normal conditions. When offshore winds weaken ahead of a cyclone, the lagoon surface can become exceptionally calm. Reflection from the sky intensifies. Depth perception becomes difficult because the water mirrors surroundings closely. The visual impression is tranquility. At the same time, underlying water levels may already be changing. Ocean water pushed by distant storm winds elsewhere in the basin begins moving toward the coastline. Tides influenced by storm pressure gradients shift subtly. These early adjustments may not produce visible waves, but can alter water depth near inlets and channels. Boat operators sometimes notice this phase as easier navigation. Reduced chop simplifies steering. Some may delay preparations because conditions seem manageable. Historically, however, rapid deterioration often follows this calm interval. Wind speed can increase sharply once outer storm bands arrive. Wildlife sometimes responds before humans notice. Fish may move away from shallow flats. Birds may alter feeding patterns or seek sheltered roosts. These behavioural changes reflect sensitivity to pressure shifts and environmental cues. Observers familiar with local wildlife sometimes recognise these signals as early indicators. Humidity typically increases during the calm phase. The air may feel heavier. Cloud patterns may appear layered rather than stormy at first. Barometric pressure readings often show gradual decline. Modern weather instruments detect these changes clearly, but casual observation may not register them. Rainfall patterns can precede strong winds. Outer rain bands may arrive while winds remain moderate. Freshwater inflow from rain affects lagoon salinity and turbidity. Sediments carried by runoff may cloud water. Nutrient input may increase. These changes interact with earlier discussed chemical dynamics. Public safety messaging often emphasizes not waiting for visible storm intensity before preparing. Lagoons illustrate why. The absence of surf inside a lagoon does not mean external storm energy is absent. It means barriers are still deflecting wave action temporarily. Emergency planning accounts for this deceptive calm. Authorities may issue evacuation or preparation notices during periods when local conditions seem stable. Compliance sometimes depends on public understanding of storm dynamics. Education about the calm before storm phenomenon helps align perception with reality. Water temperature may remain warm during this phase. Warm water fuels cyclone intensity. While this primarily concerns the storm's energy source offshore, it also affects lagoon chemistry. Warm, calm water combined with rainfall can alter stratification patterns quickly. Infrastructure around lagoons often requires early securing. Rising water levels may begin gradually before strong winds arrive. Floating docks, moored boats, and shoreline equipment benefit from preparation before conditions deteriorate. Waiting until wind increases may complicate response. Historical accounts frequently mention stillness before major storms. Mariners described unusually calm seas prior to hurricanes. Coastal communities noted quiet lagoons before sudden flooding. These observations predate modern meteorology, but align with current scientific understanding. Technological forecasting reduces uncertainty. Satellite imagery, radar, and pressure sensors track cyclone development continuously. Even when local water appears calm, forecasts may indicate imminent change. Integrating forecast information with local observation improves safety. The calm phase can also influence public psychology. People tend to respond more strongly to visible threats than predicted ones. Quiet water reduces urgency. Clear communication becomes essential to prevent complacency. Ecological consequences of cyclones extend beyond immediate flooding. Sediment redistribution, salinity shifts, and nutrient influx affect lagoon ecosystems afterward. Recovery periods vary widely. Some systems rebound quickly, others take months. Coastal geomorphology may change as well. Storm waves can reshape barriers, open new inlets, or deposit sediment in existing channels. These structural changes influence future lagoon circulation patterns. Post-storm surveys often reassess navigation routes and safety considerations. Insurance and urban planning increasingly consider lagoon-specific storm risks. Flood maps incorporate internal water level rise as well as direct ocean exposure. Building codes may reflect these risks. The calm before cyclone phenomenon demonstrates how visual cues alone can mislead. Water may appear peaceful, while atmospheric forces gather strength nearby. Recognizing this disconnect encourages reliance on broader environmental information rather than immediate appearance. This transitional calm connects closely with human activity patterns. People often intensify recreational use of lagoons during calm weather. Understanding how human interaction intersects with changing environmental conditions helps explain why risk can increase even without dramatic natural events. The period of calm water often encourages people to spend more time around lagoons. Boats go out because the surface looks manageable. Swimmers stay longer because there are no waves pushing them back to shore. Construction projects continue along waterfronts because conditions appear stable. Tourism activity tends to increase during these quiet windows. All of this adds a human layer on top of the natural processes already shaping lagoon behaviour, and that layer can intensify risk in ways that are not always obvious at the moment. Human presence changes water systems physically. Shoreline development replaces natural vegetation with hard structures such as seawalls, docks, marinas, and housing. Vegetation normally absorbs some wave energy, filters runoff, and stabilizes sediment. When it disappears, sediment can move more easily, runoff enters water more directly, and reflection of wave energy inside the lagoon increases. Reflected waves do not always look dramatic, but they create irregular water motion that complicates navigation and swimming, especially in confined basins. Urban runoff represents one of the largest human influences on lagoon chemistry. Rainwater flowing over streets, parking lots, lawns and agricultural land carries fertilizers, oils, heavy metals, plastics and organic waste. Because lagoons exchange water slowly, these materials may remain longer than they would in open coastal waters. Nutrient buildup encourages algae growth, which links back to oxygen depletion and toxic bloom formation. Chemical contaminants can accumulate in sediments, affecting marine organisms over time. Boat traffic contributes in several ways. Engines release small amounts of fuel residue. Propellers stir bottom sediments, increasing turbidity and releasing nutrients trapped in sediment layers. Wake waves reflect off lagoon boundaries, creating localized turbulence. Anchors dropped repeatedly in shallow areas damage seagrass beds that normally stabilize sediment. Each individual impact may seem small, but cumulative effects over months or years alter the lagoon environment. Recreational swimming patterns also affect conditions. Sunscreens, lotions, and personal care products wash off into the water. Most are harmless in small amounts, but high visitor density can increase chemical load. Floating equipment such as inflatable platforms may block sunlight from reaching underwater vegetation, altering photosynthesis patterns locally. Fishing activity concentrates along lagoon edges and channels where fish gather. Discarded bait, fishing line, and gear add debris. Lost gear can entangle wildlife. Overfishing in nursery areas affects population balance. Sustainable practices exist, but they depend on consistent awareness and enforcement. Aquaculture operations sometimes take advantage of calm lagoon waters. Fish farms or shrimp ponds introduce additional nutrients through feed and waste. If poorly managed, these nutrients contribute to algal growth and oxygen depletion. Well-managed systems include water exchange planning and monitoring, but not all regions maintain strict standards. Tourism infrastructure often expands quickly around lagoons because they appear safe for recreation. Resorts, restaurants, and recreational facilities cluster near sheltered water. Increased wastewater production follows. Treatment systems may struggle during peak seasons. Overflow events after heavy rain can introduce untreated sewage into lagoon water, affecting both ecology and human health. Construction modifies hydrology. Dredging deepens channels for navigation, altering current paths. Filling shallow areas for building projects reduces natural water storage capacity. Causeways and bridges restrict circulation if not designed with adequate openings. These structural changes can persist for decades. Noise pollution from boats and coastal activity affects wildlife behaviour. Fish may avoid heavily trafficked areas. Birds may relocate feeding grounds. Changes in wildlife distribution influence ecological balance. While noise does not directly endanger swimmers, it reflects broader human influence on lagoon systems. Artificial lighting along lagoon shores changes nighttime conditions. Many marine species rely on natural light cycles. Continuous artificial light can disrupt feeding or breeding patterns. Insects attracted to lights increase near shorelines, affecting both human comfort and ecological interactions. Waste management challenges increase with population density. Plastic debris accumulates easily in enclosed waters. Floating trash can obstruct drainage channels, affecting water exchange. Microplastics enter food webs through small organisms. Cleanup efforts exist but require sustained participation. Emergency preparedness sometimes lags behind development. Waterfront communities built around lagoons may underestimate flooding potential because barriers reduce visible wave impact. Stormwater drainage systems designed for typical conditions may not handle combined rainfall and surge events. Human settlement patterns therefore influence risk exposure. Recreational education varies widely. Some regions provide clear guidance about tides, currents, water quality, and wildlife. Others rely on informal knowledge. Visitors unfamiliar with local conditions may not recognize subtle hazards. Communication methods such as signage, public campaigns, and digital alerts improve awareness when implemented consistently. Economic incentives sometimes conflict with environmental caution. Businesses benefiting from tourism may emphasize calm conditions without fully explaining variability. Balanced messaging that supports both recreation and safety remains important. Climate change intersects strongly with human activity. Rising sea levels affect lagoon flushing patterns. Increased storm intensity influences barrier stability. Urban expansion continues in many coastal areas despite these changes. Long-term planning increasingly integrates environmental monitoring with development decisions. Scientific research in lagoons often focuses on cumulative effects. Individual factors such as nutrient runoff, sediment disturbance, or infrastructure alteration rarely act alone. Combined effects shape overall system behavior. Monitoring programs track multiple variables simultaneously to understand trends. Public participation plays a role in lagoon health. Community cleanup events reduce debris. Responsible boating practices limit sediment disturbance. Sustainable landscaping reduces fertilizer runoff. Each action contributes incrementally to stability. Education about personal safety integrates environmental understanding. Checking tide schedules before swimming near channels, observing weather forecasts even when water looks calm, and noting recent rainfall patterns help individuals make informed choices. These habits reduce reliance on appearance alone. Technological tools assist awareness. Mobile apps provide tide tables, weather alerts, and water quality updates. Real-time sensors in some lagoons transmit data accessible to the public. Adoption varies, but availability continues to expand. Cultural traditions sometimes preserve valuable knowledge. Fishing communities often maintain oral histories about safe channels, seasonal patterns, and storm behavior. Integrating traditional knowledge with scientific data strengthens understanding. Policy frameworks govern lagoon use in many regions. Protected areas restrict certain activities to preserve ecological function. Zoning regulations limit construction near sensitive shorelines. Enforcement effectiveness influences outcomes. Transportation infrastructure interacts with lagoons as well. Roads built along barrier islands affect sediment transport. Bridges across lagoon entrances must balance connectivity with water exchange. Engineering decisions shape hydrodynamics long after construction. Health monitoring programs consider lagoon exposure risks. After heavy rainfall or bloom events, advisories may recommend avoiding contact with water. Compliance depends on effective communication and public trust. Insurance industries increasingly analyze lagoon risk profiles. Flood history, storm exposure, and development density inform coverage decisions. These analyses indirectly encourage better planning. Scientific modelling predicts how combined human and natural factors influence lagoon evolution. Models incorporate sediment transport, sea level rise, storm frequency, and land use changes. Results inform policy and infrastructure design. Local economies depend on lagoon stability. Fisheries, tourism, recreation, and real estate all benefit from healthy conditions. Economic incentives therefore align increasingly with conservation. Personal behaviour remains central. Choosing reef-safe sunscreens, disposing of the waste properly, respecting wildlife distance, and observing safety advisories all contribute to reduced compounded risk. Understanding human influence highlights that lagoon safety is not determined solely by natural processes. Human actions modify chemistry, circulation, wildlife patterns, and infrastructure resilience. Calm water does not remove responsibility. It requires awareness of both environmental dynamics and human impact. These compounded influences also become more noticeable after sunset, when visibility decreases, navigation becomes harder, and environmental cues shift, introducing another dimension of lagoon safety considerations. Calm water creates a powerful assumption. When people see a flat surface, protected shoreline, and gentle conditions, they often classify the environment as low risk. Lagoons benefit from that perception because they contrast so strongly with rough ocean surf. The absence of crashing waves, strong visible currents, and deep offshore drop-offs leads many to treat lagoon water more like a swimming pool than a natural coastal system. That perception shapes behaviour, and behaviour influences accident patterns. Drowning statistics in coastal regions do not always match public expectation. Open ocean beaches receive much attention because wave-related rescues are visible and dramatic. Lifeguard services, warning flags, and safety campaigns often focus on surf hazards. Lagoons, sheltered bays, and estuaries sometimes receive less structured oversight. That difference in monitoring can affect how incidents occur and how they are reported. One consistent factor in drowning research is complacency. Environments perceived as safe often lead to reduced caution. People swim farther from shore. They supervise children less closely. They use flotation devices less frequently. They check weather and tide conditions less often. These behavioural shifts increase exposure even if environmental hazards are modest. Water depth variability plays a role. Lagoons frequently have gradual shallow flats interrupted by deeper channels. A person wading comfortably may step unexpectedly into deeper water. In surf zones, wave action often signals depth change visually. In calm lagoon water, the surface may not reveal the transition. Surprise contributes to panic, and panic reduces effective self-rescue. Fatigue is another contributor. Warm, calm water encourages longer swimming sessions. Without waves pushing swimmers back toward shore, outward drift may go unnoticed. By the time a swimmer decides to return, fatigue may already limit performance. Statistics show that extended time in water without rest increases drowning risk regardless of environment. Alcohol consumption appears frequently in recreational water incidents. Calm lagoon settings often host social gatherings, boating, or waterfront events. Reduced wave action may encourage swimming after drinking. Alcohol impairs judgment, balance, and swimming coordination. It also affects body temperature regulation, increasing vulnerability. Child safety patterns differ between lagoon and surf environments. Parents often remain highly alert at surf beaches because waves appear threatening. In lagoons, children may be allowed to play farther from direct supervision because conditions look gentle. Shallow areas provide false reassurance when deeper channels exist nearby. Boating incidents intersect with drowning data as well. Small craft such as kayaks, paddleboards, and dinghies are common in lagoons. Capsizing risk is lower than in rough seas, but not zero. Without life jackets, even minor accidents can escalate. Statistics consistently show higher survival rates when flotation devices are worn, regardless of water conditions. Nighttime swimming contributes to risk patterns. Lagoons near residential or tourist areas may attract evening recreation because water remains warm and calm. Reduced visibility makes orientation harder. Currents that would be visible in daylight become difficult to detect. Emergency response may also be slower at night. Medical conditions sometimes contribute. Sudden cramps, cardiac events, or breathing difficulties can occur unexpectedly. In open ocean surf, nearby lifeguards or beachgoers may notice distress quickly due to concentrated activity. Lagoon users often spread out over larger sheltered areas, delaying recognition of trouble. Data collection challenges complicate analysis. Not all regions categorize lagoon incidents separately from other coastal drownings. Terminology varies between countries. Some reports group sheltered waters with inland lakes. This variation makes precise global comparisons difficult, but regional studies often highlight similar behavioral patterns linked to perceived safety. Cultural expectations influence reporting. Communities accustomed to lagoon environments may normalize certain risks and report incidents differently. Tourist regions may emphasize prevention messaging more actively because visitor familiarity is lower. Weather conditions remain relevant even without waves. Sudden wind shifts, thunderstorms, or temperature drops can affect swimmers. Calm conditions earlier in the day may change rapidly. Without the visual cue of incoming surf, weather transitions may catch people off guard. Currents discussed earlier continue to influence drowning patterns. Outflow through lagoon inlets, wind-driven drift and tidal exchange create horizontal movement. Even moderate current combined with fatigue can overwhelm swimmers. Because these currents lack dramatic wave markers, people may underestimate them. Rescue infrastructure varies widely. Some lagoons have lifeguards, patrol boats, and clear signage. Others rely on informal supervision. Response time affects outcomes significantly. Quick assistance often determines survival in water emergencies. Public education campaigns increasingly address the myth of safer water. Messaging emphasizes that calm appearance does not eliminate natural variability. Simple precautions such as swimming with companions, checking local conditions, and wearing flotation during boating reduce risks substantially. Technology contributes to prevention. Personal locator beacons, waterproof communication devices, and wearable flotation aids improve safety margins. Adoption remains uneven, often influenced by cost and awareness. Urban design around lagoons influences accessibility. Easy shoreline access increases recreational use. Safe access design includes clear entry points, signage, and rescue equipment availability. Poorly planned access may encourage entry in unsafe locations. Historical case studies illustrate patterns. Some coastal cities built around lagoons report higher drowning incidents in sheltered waters than in exposed surf zones. Researchers attribute this partly to exposure frequency and partly to behavioural assumptions. Seasonal variation exists. Tourist seasons with peak lagoon use often coincide with warm, calm weather, increasing exposure. Local residents may have more experience interpreting conditions, while visitors rely on visual cues. Water clarity affects risk perception. Clear water invites swimming. Turbid water sometimes deters it. Yet clarity does not correlate directly with safety. Currents, depth, and chemistry remain independent factors. Equipment availability matters. Life rings, rescue poles, and emergency call points improve response. Some lagoon parks install these routinely. Others rely on informal community assistance. Training programs for waterfront businesses increasingly include water safety education. Staff awareness improves early intervention capacity. Hotels, marinas, and tour operators play roles in disseminating safety information. Scientific literature often emphasizes multi-factor causation. No single element explains drowning patterns. Environmental conditions, human behavior, infrastructure, and communication interact. Understanding this interaction helps refine prevention strategies. Public perception continues evolving. As awareness grows, the myth of universally safer calm water becomes less dominant. Balanced understanding encourages enjoyment with informed caution rather than fear. These statistical and behavioural insights highlight how perception shapes outcomes. Calm appearance encourages activity. Activity increases exposure, and exposure interacts with environmental variability. The next aspect to consider involves how visibility changes after sunset, when calm water remains inviting, but environmental cues diminish further. As daylight fades around a lagoon, the environment does not suddenly become more dangerous, but the way people perceive it changes significantly. Visibility drops first, then contrast, then depth perception. The same water that seemed transparent and easy to read during the day becomes reflective and uncertain. Lights from nearby buildings or boats shimmer across the surface, sometimes masking subtle movement. Calm water reflects light very efficiently, so at night it often looks darker, smoother, and more uniform than it actually is. Human vision adapts slowly to low light. During that adjustment period, details disappear. Shallow areas may appear deeper. Deeper channels may appear uniform with surrounding flats. Without strong wave action to indicate depth changes, Swimmers and boaters rely heavily on visual cues that are no longer reliable. A shoreline that felt close in daylight may appear farther or closer than it actually is due to reflection and shadow. Temperature also changes perception at night. Lagoon water tends to retain heat after sunset, sometimes remaining warmer than surrounding air. That warmth invites evening swimming or boating. The comfort can reduce caution. People may enter water without the same preparatory checks they would make during the day. Navigation becomes more complex, even for experienced boaters. Marker buoys, channel posts, and reef indicators may be difficult to see without proper lighting. Reflections from shore lights can obscure navigation lights. Calm water reduces sound cues because there is little wave noise. Boats moving slowly may be harder to detect acoustically. Currents discussed earlier do not stop after sunset. Tidal exchange continues. Wind-driven flow may persist even if winds weaken. Without daylight reference points, gradual drift becomes harder to notice. A swimmer floating comfortably may move farther than intended before recognizing displacement. Wildlife activity often increases at night. Many fish feed more actively in low light. Crustaceans leave burrows. Some jellyfish rise closer to the surface. None of this implies aggression, but it does increase the chance of unexpected contact. Reduced visibility makes avoidance more difficult. Insect activity near lagoon edges often increases after dark, particularly in warmer climates. While not directly a water hazard, insects influence comfort and attention. Distraction can reduce awareness of surroundings. Artificial lighting changes the environment unevenly. Brightly lit marinas or waterfronts contrast sharply with darker stretches of shoreline. Eyes adjust to bright areas, reducing sensitivity to darker zones. This adaptation delay affects reaction time if someone moves from lit areas into darker water. Emergency response can take longer at night. Fewer people may be present to notice distress. Visibility challenges affect rescue personnel as well. Locating a swimmer in calm, dark water without reflective gear can be difficult. Sound behaves differently over water at night. Temperature inversions can carry sound farther. Voices or boat engines may seem closer or farther than they actually are. This acoustic distortion complicates orientation. Weather changes sometimes occur overnight. Calm evening conditions can shift to stronger winds before dawn. Boats anchored assuming continued calm may encounter unexpected movement. Awareness of overnight forecasts helps anticipate such changes. Psychological factors also play a role. Calm water at night can feel peaceful and private. That feeling encourages relaxation but may reduce vigilance. People may swim alone more often at night than during the day, increasing risk if problems arise. Technology helps mitigate some of these challenges. Waterproof lights, reflective flotation devices, GPS tracking apps, and communication tools improve visibility and orientation. Adoption varies widely depending on awareness and resources. Local regulations sometimes restrict nighttime swimming or boating in certain lagoon areas, particularly where navigation hazards or wildlife concerns exist. Compliance depends on clear signage and community education. Cultural practices influence nighttime lagoon use. In some regions, evening fishing or social gatherings around lagoons are traditional. Community familiarity with conditions can reduce risk, though visitors may not share that familiarity. Water quality conditions can change after sunset. Photosynthesis stops in darkness, reducing oxygen production by aquatic plants. Oxygen consumption continues, sometimes lowering levels slightly overnight. These changes are usually minor but illustrate ongoing chemical dynamics independent of visibility. Reflective calm water can distort spatial orientation. The boundary between water and sky becomes less distinct. This can cause disorientation for swimmers far from shore. Floating on the back while looking upward may make it difficult to judge direction. Life-saving equipment visibility matters more at night. Clearly marked rescue rings, illuminated call points, and accessible flotation devices improve response capability. Some waterfronts install solar-powered lighting specifically for safety. training for nighttime water safety emphasizes buddy systems, flotation use, and avoidance of alcohol. These guidelines mirror daytime safety, but carry greater importance when visibility is reduced. Nighttime also affects sediment disturbance visibility. If a swimmer steps into soft sediment, turbidity increases but may not be visible in low light. Loss of footing can surprise even experienced swimmers. Cameras and surveillance systems sometimes monitor lagoon waterfronts. These tools assist emergency response but depend on proper maintenance and community awareness. Insurance and liability considerations often include nighttime access policies. Property owners and municipalities evaluate lighting, signage, and access control to manage risk. Scientific monitoring continues overnight. Automated sensors record temperature, salinity, oxygen, and currents continuously. Data show that lagoon processes do not pause with daylight changes. Public messaging often emphasizes that calm night water requires the same respect as daytime conditions. Visual tranquility does not eliminate natural variability. Understanding nighttime lagoon dynamics builds on earlier discussions of perception, chemistry, currents, and wildlife. Reduced visibility amplifies the influence of those factors rather than replacing them. These nighttime considerations connect closely with physical water behavior, particularly how waves and pressure interact within confined spaces, which shapes another dimension of lagoon safety. Water pressure is usually discussed in terms of depth. The deeper you go, the greater the pressure from the weight of water above. That principle applies everywhere, from swimming pools to the deepest ocean trenches. In lagoons, depth-related pressure is often modest because many lagoons are shallow. Yet pressure inside a lagoon is influenced not only by depth, but also by confinement. When water is partially enclosed, pressure gradients develop horizontally as well as vertically. These gradients drive movement and influence how energy behaves within the basin. In open ocean settings, when wind pushes water toward a coastline, the displaced water can spread laterally over wide distances. In a lagoon, barriers restrict that lateral spread. If wind pushes water toward one side of the lagoon, it cannot escape outward through the barrier except at specific openings. This creates slight differences in water level across the basin. Even a few centimeters of difference can produce measurable pressure gradients. Water moves from higher level to lower level in response. The physics is straightforward. Pressure at a given point in water depends on depth and the height of the water column above it. If one part of the lagoon surface rises slightly higher than another due to wind or surge, pressure increases proportionally beneath that higher surface. Water responds by flowing toward areas of lower pressure. In a confined basin, that flow concentrates through narrow passages or deeper channels. These pressure-driven flows may not generate visible waves. They manifest as steady currents, sometimes subtle at the surface, but stronger at depth. Because lagoons are shallow, pressure differences required to initiate flow are small compared to deep ocean basins. This sensitivity means that modest environmental changes can produce noticeable current shifts. Wave reflection adds complexity. When waves enter a lagoon through an inlet or pass, they encounter shorelines and structures. Instead of continuing outward across vast open water, they reflect. Reflected waves intersect with incoming waves, producing interference patterns. In some geometries, this can create standing waves, where water oscillates in place rather than travelling continuously. These oscillations alter local pressure periodically. Standing waves in lagoons are often low in amplitude but can influence water level along shorelines rhythmically. In elongated lagoons, wind blowing along the length can push water toward one end. When wind decreases, water sloshes back. This oscillation, called a seach, results from pressure imbalance created by confinement. While usually mild, seaches demonstrate how confined geometry shapes water motion, independently of external waves. Channel constrictions amplify pressure effects. When water moves from a broad shallow area into a narrow deeper channel, the cross-sectional area decreases. To maintain flow continuity, velocity increases. Faster flow corresponds to dynamic pressure changes. Swimmers entering such channels may feel a sudden increase in force, even though surface conditions appear unchanged. Storm surge dynamics illustrate confined pressure clearly. As external sea level rises due to wind and atmospheric pressure changes, water enters the lagoon. If outlets are limited, water accumulates until internal pressure matches external pressure. This accumulation raises lagoon water level, sometimes above surrounding land elevations. The rise may occur without large waves, driven primarily by pressure gradients rather than surface turbulence. Atmospheric pressure also influences lagoon water directly. Lower atmospheric pressure during storms allows water to expand upward slightly. In a confined lagoon, this effect adds to surge-driven rise. The combined influence of atmospheric and wind-driven pressure can produce water level increases disproportionate to local wave height. Groundwater interactions provide another example. In some coastal regions, pressure differences between lagoon water and adjacent aquifers drive subsurface flow. High lagoon levels during storms may push saline water into groundwater systems. Conversely, fresh water may seep into lagoons when groundwater pressure exceeds lagoon water pressure. These exchanges reflect pressure balancing beyond visible surface conditions. Temperature-induced density changes interact with pressure as well. Warmer water is less dense, so pressure at depth differs slightly compared to cooler water at the same depth. When stratification exists, internal pressure gradients can form along density boundaries. Internal waves may travel along these boundaries beneath the surface. These internal waves are rarely visible but represent energy movement confined within the lagoon. Infrastructure responds to confined water pressure too. Seawalls and docks experience forces not only from wave impact, but also from sustained water level differences. Drainage systems must handle pressure-driven inflow during heavy rainfall combined with high lagoon levels. Engineering designs account for hydrostatic and hydrodynamic pressures in enclosed basins. Boat moorings illustrate pressure effects practically. During tidal changes, water level differences across narrow entrances generate currents that strain anchor lines. Operators sometimes observe that boats in lagoons swing in specific patterns during tidal exchange. These patterns reflect underlying pressure-driven flow rather than wind alone. Human perception often equates pressure with dramatic depth. In lagoons, the more relevant concept is gradient rather than magnitude. Small gradients across short distances produce motion because confinement restricts alternative pathways. Recognizing this principle helps explain why calm, shallow water can still exert persistent force. Measurement instruments confirm these dynamics. Tide gauges placed at different points within a lagoon often record slight time lags in water level changes. These lags reflect how pressure equalizes gradually through narrow inlets. Current meters show acceleration through constricted passages corresponding to those pressure differences. Environmental management sometimes modifies pressure relationships intentionally. Opening additional inlets increases exchange and reduces internal pressure buildup during storms. However, increasing exchange may alter salinity and ecological balance. Management decisions therefore weigh flood risk against ecological stability. Pressure effects influence sediment transport. Stronger flow through channels during tidal exchange scours sediment, deepening some areas while depositing material elsewhere. These changes alter basin shape over time, influencing future pressure-driven flow patterns. Climate factors again interact. Sea level rise raises baseline pressure conditions in lagoons. Higher baseline levels mean smaller additional pressure increases can lead to flooding. Adaptive planning increasingly considers these cumulative effects. Recreation intersects subtly with pressure-driven movement. Swimmers near inlets during falling tide may feel outward flow generated by pressure equalization. Without wave cues, the force may seem unexpected. Understanding the gradient concept clarifies that movement originates from water seeking balance. Scientific study of confined water pressure integrates hydrodynamics, meteorology, and coastal engineering. Computer models simulate how small-level differences propagate through complex lagoon geometries. These models assist in flood forecasting and infrastructure design. Education about confined pressure emphasizes that visible calm does not equal static conditions. Water constantly adjusts to gravity, wind, and atmospheric influences. In a constrained basin, those adjustments create focused flows. Recognizing the science of confined water pressure provides a framework for comparing lagoon behavior with the open ocean. Despite the ocean's scale and visible power, its vastness allows energy distribution. Lagoons, by contrast, localize and channel energy within defined boundaries. When people imagine danger at sea, the open ocean usually comes to mind first. Vast horizons, deep water, large waves, powerful storms. The scale alone feels intimidating. By contrast, a lagoon appears modest. It has visible boundaries. The far shore is often within sight. Waves are small or absent. Depth is typically manageable. On the surface, the comparison seems straightforward. Open ocean equals high risk, lagoon equals lower risk. Yet when examined carefully, the differences are more nuanced, and in certain situations the smaller, calmer environment can present risks that are less obvious but more concentrated. The open ocean distributes energy across immense distances. Wind-generated waves travel outward, spreading their force. Currents such as major ocean gyres move enormous volumes of water, but they do so across thousands of kilometers. Even storm systems, while powerful, interact with a broad water mass that can absorb and redistribute energy gradually. In this context, hazards are often visible. Breaking waves signal turbulence. Large swells indicate changing weather. Depth changes are marked by surface texture and color shifts. The scale itself communicates caution. Lagoons function differently because of confinement. Energy that enters does not have the same space to spread. Barriers restrict lateral movement. Channels focus tidal exchange. Wind-driven surface water accumulates against boundaries. Small differences in water level translate into concentrated flow through limited openings. In effect, while the open ocean disperses energy, lagoons channel it. Visibility of hazard is another key contrast. In the open ocean, wave height and direction provide constant feedback. Swimmers feel push and pull from surf. Boaters adjust to swell patterns. In lagoons, surface calm reduces that feedback. Currents may exist without visible wave indicators. Depth changes may not create surface disturbance. This lack of visual cues shifts risk from obvious to subtle. Water chemistry varies more in lagoons. The open ocean maintains relatively stable salinity and temperature in most surface regions. While local variation occurs, large-scale mixing moderates extremes. Lagoons, due to limited exchange, experience faster swings in salinity, temperature and oxygen levels. These shifts influence ecological balance and sometimes water quality. From a human safety perspective, this variability may not produce immediate danger, but it contributes to unpredictable conditions. Biological distribution differs as well. The open ocean supports large migratory species, some of which command public attention. Lagoons support concentrated populations of juvenile fish, invertebrates, and microorganisms. Density of smaller organisms can be higher in lagoons due to nutrient retention. Encounters with wildlife are shaped more by concentration than by size. In open ocean settings, biodiversity is high but spread across space. In lagoons, biodiversity can be intense within a small area. Storm interaction highlights further differences. In open ocean exposure zones, storm waves are powerful and destructive. The hazard is direct and visible. In lagoons, barriers reduce wave height but may trap rising water levels. Flooding can extend over wide, shallow areas without dramatic surf. The absence of large waves does not equate to absence of storm risk. Instead, risk manifests as sustained water level rise and concentrated currents through inlets. Human behavior adapts to perception. people often approach open ocean beaches with heightened caution. Lifeguards are common, warning flags are recognised, swimming areas may be restricted. In lagoons, fewer overt warnings exist because the environment appears controlled. Reduced vigilance increases exposure frequency. Statistical analyses in some coastal regions suggest that sheltered waters can account for a significant portion of drowning incidents, precisely because activity levels are higher relative to perceived risk. Thermal patterns differ too. Open ocean water changes temperature gradually due to depth and mixing. Lagoons, being shallow, heat and cool quickly. Warm water encourages longer recreational use. Extended exposure increases fatigue potential. Warmth also influences microbial growth rates, affecting water quality. Navigation considerations present another contrast. Large vessels operate in the open ocean with substantial clearance and predictable channels. Small craft in lagoons must contend with shifting sandbars, narrow passages and variable depth. A grounded boat in a lagoon may not face towering waves, but rapid tidal shifts can leave vessels stranded or stressed against obstacles. Acoustic perception differs as well. In open ocean conditions, wave noise masks subtle environmental sounds. In lagoons, quiet water enhances sound reflection. This can make boats seem closer than they are or distort distance perception at night. While not a primary safety factor, it influences situational awareness. Emergency response infrastructure varies by setting. Surf beaches in many regions maintain dedicated lifeguard services. Lagoons may rely on less formal oversight. The disparity reflects historical focus on visible surf hazards rather than enclosed water dynamics. Psychological framing remains central. Open ocean risk is dramatic and cinematic. Lagoon risk is incremental and contextual. The latter can be underestimated because it lacks spectacle. Yet incremental risk, repeated frequently, accumulates. From an engineering perspective, open ocean coastal defences focus on wave energy absorption and structural reinforcement. Lagoon management often focuses on circulation, water quality, and flood control. These priorities reflect the distinct physical behaviours of each environment. Cultural narratives reinforce comparison. Literature and media portray the open sea as adventurous and dangerous. Lagoons appear serene and idyllic. This narrative shapes public expectation long before individuals encounter either environment directly. Scientific monitoring in open ocean settings often tracks large-scale phenomena such as hurricanes, currents, and temperature anomalies. Lagoon monitoring focuses on localized variables such as nutrient levels, oxygen concentration, and salinity. The scale of observation mirrors the scale of physical processes. Economic activities differ. Offshore fishing, shipping, and energy extraction dominate open ocean use. Tourism, small-scale fishing, and waterfront living dominate lagoon use. Each activity carries unique risk profiles. Education about water safety increasingly emphasizes context-specific guidance. Understanding that both environments require awareness, though for different reasons, supports balanced decision-making. The open ocean demands respect for visible power. Lagoons demand attention to subtle variability and confined dynamics. The comparison does not suggest that lagoons are inherently more dangerous than the open ocean in every situation. Rather, it shows that danger manifests differently. Open ocean hazards are broad and apparent. Lagoon hazards are localized and often concealed within calmness. Recognizing this contrast clarifies why historical accounts sometimes describe unexpected incidents in sheltered waters. These stories often begin with calm conditions and end with realization that calmness masked complexity. Understanding those patterns benefits from looking at documented events and lessons drawn from them. Historical experience with lagoons shows a consistent pattern. Events rarely begin with obvious danger. They often start with ordinary activity, calm water, and familiar surroundings. Only later do people recognize that a combination of environmental factors, human behavior, and structural conditions created risk that was not immediately visible. Studying these past situations helps clarify how lagoon environments behave over time and why awareness matters even when water appears tranquil. Coastal settlements have long favoured lagoons because of their sheltered nature. Ancient trading ports frequently developed behind sandbars or reefs, where ships could anchor away from strong ocean swell. Archaeological evidence from Mediterranean, Pacific and Southeast Asian regions shows that early communities understood the benefits of protection from waves. At the same time, historical records describe periodic flooding, navigation difficulties, and water quality changes. The protective barrier that enabled settlement also introduced complexity. Venice provides a well-documented example of long-term lagoon interaction. The Venetian lagoon formed through sediment deposition and tidal exchange with the Adriatic Sea. Over centuries, residents modified channels, built barriers, and adjusted water management practices to maintain navigation and reduce flooding. Historical chronicles describe repeated high water events where calm lagoon surfaces rose gradually rather than violently. These events highlighted how enclosed water can accumulate energy quietly until thresholds are reached. In tropical atoll regions, oral histories passed through generations often include guidance about reef passes and tidal timing. Islanders learned through experience that calm lagoon water near passes could conceal strong outward currents during ebb tide. Navigation traditions incorporated timing knowledge to avoid hazardous flow periods. These cultural lessons emerged from repeated observation rather than isolated incidents. Colonial-era maritime logs also reference lagoon challenges. Explorers entering unfamiliar atolls sometimes misjudged inlet currents, grounding vessels or drifting toward reef edges. Calm interior water gave a sense of security, yet restricted exits complicated navigation. These historical records contributed to modern charting practices that mark reef passes carefully. Storm-related lagoon flooding appears frequently in coastal history. Before modern meteorology, communities sometimes interpreted calm pre-storm water as a sign of safety. Accounts from Caribbean and Pacific islands describe periods of unusual stillness, followed by rapid water level rise once storm surge entered enclosed basins. Flooding often extended farther inland around lagoons than along exposed surf beaches, because water had fewer escape routes. Industrial development in the 19th and 20th centuries introduced new dimensions. Ports expanded within lagoons to take advantage of sheltered conditions. Dredging altered circulation patterns. Some historical case studies show that poorly planned dredging increased stagnation, leading to water quality decline and ecological stress. Later restoration efforts sought to restore natural exchange. Aquaculture history offers additional lessons. Early shrimp farming projects in coastal lagoons sometimes increased nutrient loading without adequate flushing. Documented fish mortality events and water quality degradation led to revised management practices emphasizing controlled feeding, waste management and monitoring. Public health history intersects as well. Records from various coastal cities note periods when lagoon water quality declined due to urban runoff or sewage discharge. Illness outbreaks prompted infrastructure improvements such as wastewater treatment facilities and stricter discharge regulations. These developments highlight how human activity interacts with confined water chemistry. Navigation safety improved over time as hydrographic surveys mapped lagoon depths and channels. Earlier mariners relied on visual cues and local knowledge. Modern charts include current predictions, depth contours, and hazard markers. These tools reduce uncertainty but require awareness and usage. Case studies from tourist regions show recurring themes. Visitors unfamiliar with local tidal patterns sometimes drifted toward lagoon inlets during calm conditions. Rescue services expanded education efforts afterward. Signage, public announcements, and digital alerts became more common responses. Environmental conservation history also provides insight. Mangrove removal in several regions during 20th century development increased sediment mobility and reduced natural filtration. Subsequent restoration projects demonstrated improved water clarity and reduced nutrient accumulation. Historical comparison showed measurable ecological benefits from restoring natural barriers. Climate-related historical analysis indicates shifting patterns. Sea level rise documented over decades has altered lagoon boundaries in some regions. Formerly dry land may now flood during high tides. Historical shoreline maps compared with modern surveys illustrate gradual change that influences current risk assessments. Scientific research history contributes too. Early oceanographic studies focused on open ocean dynamics. Later research recognized lagoons as distinct systems requiring dedicated investigation. Long-term monitoring programs established in the late 20th century now provide datasets showing seasonal and multi-year variability in salinity, temperature, oxygen, and biological activity. Cultural storytelling remains a valuable historical resource. Fishing communities often maintain detailed memory of unusual events, seasonal patterns, and safe practices. These narratives complement scientific data by providing context and continuity. Insurance records and urban planning documents offer another perspective. Areas with repeated lagoon flooding events often revise building codes, drainage design, and emergency planning. Historical loss data inform modern infrastructure decisions. Educational programs evolve from historical incidents. Water safety campaigns increasingly include lagoon-specific guidance. Recognition that calm water does not eliminate hazards shifted messaging strategies. Technological advances also reflect lessons learned. Remote sensing, automated sensors, and predictive modelling arose partly from the need to understand confined coastal systems better. These tools now inform daily management decisions. The recurring theme across historical examples is not catastrophe, but accumulation. Small factors combine: restricted circulation, weather variability, human development, biological response. Each factor alone may seem manageable. Together they shape lagoon behaviour over time. Historical awareness encourages balanced perspective. Lagoons remain valuable ecological, cultural and recreational environments. Understanding their complexity enhances appreciation rather than diminishing it. Looking back at past experiences naturally leads toward reflection on how these environments should be approached today, especially considering both their calm appearance and their dynamic underlying processes. Looking back across everything we explored, the lagoon stops feeling like a simple patch of quiet water and starts resembling a living intersection. It sits between forces rather than apart from them. Ocean tides, river runoff, atmospheric pressure, sediment transport, wildlife cycles, and human activity all meet there. None of these influences pause just because the surface appears calm. That steady interaction is what gives lagoons their character and also what makes them easy to misinterpret. The calm surface is often the first thing people notice, but it is rarely the most informative feature. Depth variation, current direction, recent rainfall, tidal timing, wind patterns, and shoreline configuration usually tell more about how the water is behaving. Those details are not dramatic, yet they explain why conditions shift even when nothing obvious seems to change. The more attention moves from appearance to process, the easier it becomes to understand what is happening in the water. Historical experience shows that people who live near lagoons long enough tend to adopt observational habits. They watch how floating debris drifts. They notice how bird activity changes before storms. They remember which inlets strengthen during falling tide. These habits develop gradually. They are rarely formal lessons. They come from repeated exposure to a system that rewards attentiveness. Modern technology adds another layer without replacing observation. Tide apps, satellite weather forecasts, water quality reports, and automated sensors provide information earlier and more precisely than previous generations had. Used together with simple observation, they make lagoon environments more predictable. Ignoring them while relying solely on visual calmness removes that advantage. the connection between ancient coastal history and modern lagoon behaviour is direct. Many lagoons formed thousands of years ago as sea level stabilised after glacial periods. Coral reefs grew upward towards sunlight. Sandbars formed through persistent wave and current action. Mangrove forests expanded along sheltered edges. These geological and biological processes continue slowly even now. What appears static in a human lifetime is part of a much longer timeline. Understanding that longer timeline changes perspective. A lagoon is not a fixed object. It is a stage in an ongoing coastal evolution. Channels migrate. Barriers shift. Salinity patterns fluctuate. Wildlife populations adapt. Human infrastructure adds another layer of change. Seeing the lagoon as dynamic rather than permanent helps explain why conditions sometimes differ from memory or expectation. Human interaction has accelerated certain changes. Urban development increases runoff. Dredging alters depth and circulation. Tourism raises seasonal pressure on water quality. At the same time, restoration projects in many regions are improving tidal exchange, replanting mangroves, and reducing pollution sources. These efforts show that lagoon systems respond to management decisions as well as natural forces. Climate variability is becoming a larger influence. Sea level rise affects flushing efficiency. Changing rainfall patterns alter salinity balance. Temperature trends influence biological growth cycles. None of these changes eliminate lagoons, but they adjust how they function. Awareness of these trends helps explain why long-term observation matters. Wildlife presence continues to reflect lagoon health. Fish nurseries, bird feeding grounds, seagrass coverage, and coral vitality all provide indirect signals about water conditions. Observing these biological indicators often reveals changes before formal measurements do. Communities that maintain close relationships with lagoon ecosystems frequently detect subtle shifts earlier. Chemical conditions remain equally important. Oxygen levels, nutrient concentration, and salinity balance shape ecological stability. Calm water can coexist with chemical variability. Recognizing that distinction encourages more informed recreational choices, particularly after heavy rain, storms, or extended heat. Human safety considerations follow the same principle. Calm appearance does not remove the need for situational awareness. Checking tide timing, noting wind direction, understanding recent weather, and recognizing inlet locations all contribute to safer interaction. These habits become routine with experience. Nighttime, storm approach, seasonal shifts, and wildlife cycles all interact with lagoon behavior. None of these factors operate independently. A warm evening after rainfall during an outgoing tide presents different conditions than a cool morning after steady winds during incoming tide. Context determines experience. Cultural knowledge remains valuable alongside scientific data. Fishing traditions, navigation habits, and local storytelling often preserve practical insights. Combining traditional knowledge with modern monitoring provides a fuller understanding than either alone. Economic reliance on lagoons continues globally. Fisheries, tourism, transportation, and residential development depend on their sheltered character. Maintaining ecological balance therefore has practical as well as environmental importance. Water quality, sediment stability, and flood resilience affect livelihoods directly. Education increasingly emphasizes systems thinking. Instead of treating lagoons as isolated swimming areas, they are presented as interconnected coastal environments. This approach helps people appreciate both their beauty and their complexity without framing them as dangerous by default. Personal awareness fits into that broader picture. Observing before entering the water, respecting local advisories, and recognizing environmental variability become simple habits rather than burdens. These habits support both enjoyment and safety. Technological monitoring will likely expand further. Remote sensing, automated water chemistry analysis, and predictive modelling continue improving. These tools help anticipate changes rather than reacting afterward. Access to such information is becoming more widespread. Long-term sustainability depends on balancing access with preservation. Lagoons invite recreation because they are calm. Protecting the factors that create that calm, healthy reefs, stable barriers, functioning wetlands, ensures continued usability. The relationship between humans and lagoons reflects a broader relationship with coastal environments. Appreciation grows with understanding. Understanding grows with observation. Observation encourages respect. That respect does not require alarm or hesitation. It simply means recognizing that quiet water carries history, motion, chemistry, biology, and human influence all at once. When those layers are acknowledged, the lagoon becomes more than a scenic backdrop. It becomes an environment that rewards attention and offers insight into how land and sea interact continuously.